The universe had a beginning. That's what we've been told our entire lives. 13.8 billion years ago, everything that has ever existed or will ever exist exploded into being from a point smaller than an atom. Before that, nothing. Just pure, absolute nothingness. No space, no time, no matter, no energy, just nothing. And then suddenly, for no reason, everything, the Big Bang, the moment of creation, the beginning of all beginnings. Except there's a problem. Scientists have been finding things that shouldn't be possible according to that story. Things that predate what should be the starting point. Things that carry signatures from before the universe supposedly began. And the more we look, the more uncomfortable the evidence becomes. Because what if the Big Bang wasn't the beginning at all? What if it was just a transition, a phase change, one moment in a story that has no first page? We're going to take a deep dive into the most unsettling question in all of cosmology. Not what caused the Big Bang, but what was already there before it happened. We're going to examine ancient crystals on Earth that remember events from before they should have existed. We're going to explore the possibility that entire civilizations could have risen and fallen without leaving traces we'd recognize. We're going to look at planetary catastrophes that reset the geological record so thoroughly that entire epochs of history become invisible. And we're going to confront the deeply disturbing possibility that when the universe began, whenever and however that actually happened, something was already waiting. The evidence is there. It's been staring us in the face this whole time. We just didn't know how to read it, until now. So let's start with the Big Bang itself and the shadow it casts over everything we think we know about existence. The Big Bang's shadow. When nothing was something, so let's talk about the Big Bang. You know, that thing we were all taught in school as the ultimate beginning, the point where everything started, the moment where the universe just popped into existence from literally nothing. It's the prevailing theory of how our universe came to be, and for the most part, it's pretty well accepted by the scientific community. But here's the thing that's been keeping me up at night ever since I started researching this video. What if the Big Bang wasn't actually the beginning? What if there was something before it? And I'm not talking about some fringe conspiracy theory here. I'm talking about legitimate scientific discoveries that suggest the very foundations of what we understand about the origin of the universe might be fundamentally flawed. Now, before we get into the really weird stuff, and trust me, we're going to get into some genuinely mind-bending territory in this video, we need to establish what the Big Bang actually is and why it's been the cornerstone of cosmology for nearly a century. Because if we're going to challenge it, we need to understand it first. And I know a lot of you probably already know this stuff, but bear with me because there are some details here that are going to be crucial when we start pulling this thread. The Big Bang theory, at its core, suggests that the universe expanded from an incredibly hot and dense state approximately 13.8 billion years ago. That's not a typo, 13.8 billion years. That's a number so incomprehensibly large that our brains basically just shut down when we try to process it. But that's what the data tells us. This isn't some wild guess either. This is based on decades of observations, measurements, and some of the most sophisticated scientific instruments humanity has ever created. NASA's Planck satellite, the Hubble Space Telescope, countless other missions have all contributed to refining this number, and they all point to the same basic timeline. But let's rewind a bit. How did we even figure this out? Well, it all starts with a guy named Edwin Hubble. Not the telescope, the actual person the telescope was named after. Back in 1929, Hubble made an observation that would fundamentally change our understanding of the universe. He noticed that galaxies were moving away from us, and not just moving away, but the farther away they were, the faster they were moving. This became known as Hubble's law, and it was the first real concrete evidence that the universe was expanding. Now, if the universe is expanding today, that means if you rewind the clock, it was smaller yesterday, and smaller the day before that. And if you keep rewinding, eventually you get to a point where everything, and I mean everything, all the matter and energy in the entire universe was condensed into an infinitesimally small point. That's the Big Bang. But it's not like there was some kind of explosion in space. This is probably the most misunderstood aspect of the Big Bang, and it drives physicists absolutely insane when people get it wrong. The Big Bang wasn't an explosion that happened somewhere in space. It was the expansion of space itself. There was no center point, there was no edge. The Big Bang happened everywhere at once because everywhere was the same point. I know that sounds like complete nonsense, but that's genuinely what the evidence suggests. The universe doesn't have a center or an edge. It never did. When the Big Bang occurred, it occurred simultaneously at every point in space because space itself was being created in that moment. Now, one of the most compelling pieces of evidence for the Big Bang is something called the cosmic microwave background, or CMB for short. This is basically the afterglow of the Big Bang, the leftover radiation from when the universe was young and hot. About 380,000 years after the Big Bang, the universe had cooled down enough for atoms to form, and light was able to travel freely for the first time. That light has been traveling through space ever since, and we can still detect it today. It's everywhere. No matter where you point your telescope in the sky, you'll find this faint microwave radiation. It was discovered accidentally in 1965 by two physicists named Arno Penzias and Robert Wilson. They were trying to eliminate background noise from their radio antenna and kept picking up this persistent signal. Turns out, they'd stumbled upon one of the most important discoveries in the history of cosmology. They won a Nobel Prize for it in 1978, and rightfully so, because the CMB basically cemented the Big Bang theory as the best model we have for the origin of the universe. The CMB also tells us something else that's absolutely crucial. When scientists mapped it using satellites like WMAP and Planck, they found that it wasn't perfectly uniform. There were tiny fluctuations in temperature, variations of about 1 part in 30,000. These fluctuations are incredibly important because they represent the seeds of all the structure we see in the universe today. Those tiny differences in density eventually grew into galaxies, stars, planets, and ultimately us. Without those initial fluctuations, the universe would have remained a uniform, boring soup of particles with no structure whatsoever, no galaxies, no stars, no planets, no life, nothing. Now let's talk about what happened in those first moments after the Big Bang, because this is where things get really interesting. In the very early universe, within the first few minutes, something called Big Bang nucleosynthesis occurred. This is the process where the first atomic nuclei were formed. Hydrogen and helium, the two lightest elements, were created in these first few minutes. And here's the kicker. The ratio was about 75% hydrogen and 25% helium. This was predicted back in the 1940s by physicists Ralph Alpha and George Gamow, and when we actually went out and measured the abundance of these elements in the universe, guess what? It matched their predictions almost perfectly. That's not a coincidence. That's the Big Bang theory making accurate, testable predictions that were later confirmed by observation. This is how science works at its best. But for all its success, for all the evidence supporting it, the Big Bang theory has always had this nagging problem that scientists have been grappling with since the beginning. And it's not a small problem. It's a fundamental philosophical problem that strikes at the very heart of what we understand about existence itself. If the universe had a beginning, what came before? What was there before time and space existed? What does it even mean for something to come before time, if time itself didn't exist yet? For a long time, The answer from the scientific community was essentially nothing. There was nothing before the Big Bang because there was no before. Time and space were created in the Big Bang, so asking what came before is like asking what's north of the North Pole. It's a nonsensical question because there is no north of the North Pole. The concept doesn't apply. This is sometimes called the cosmic censorship theorem, and it's been a convenient way to sidestep the question of origins without having to deal with the uncomfortable philosophical implications. But let's think about that for a second. Nothing. True nothingness. Not the absence of something, but the absence of everything. No space, no time, no matter, no energy, no physical laws, no quantum fields, no anything, just pure, absolute nothingness. And then suddenly, from this nothingness, the entire universe springs into existence. Everything that has ever existed or will ever exist, all of it, just appears from nowhere for no reason. Does that actually make sense? Can something genuinely come from nothing, or is nothing itself something we fundamentally misunderstand? Philosophers have been arguing about this for millennia. The ancient Greeks debated whether a true void could even exist. Medieval theologians wrestled with the idea of creation ex nihilo, creation from nothing, and whether that required divine intervention. And now, modern physicists are finding that the more we learn about the universe, the more we realize that nothing might not be what we think it is. Here's where things start to get weird. In quantum mechanics, which is the study of the very small, the subatomic realm, there's this concept called quantum fluctuations. Even in what we would call empty space, a perfect vacuum with no particles in it, there's still something going on. Virtual particles are constantly popping in and out of existence. They appear, exist for an infinitesimally small amount of time, and then disappear. This has been observed. This is real. We've measured it. The Casimir effect, for example, is a direct consequence of these quantum fluctuations, and it's been experimentally verified. So even what we call empty space, nothingness, isn't actually empty at all. It's seething with activity at the quantum level. This raises a really uncomfortable question. If empty space isn't truly empty, was the nothing before the Big Bang truly nothing? Or was it something? Some kind of pre-existing quantum state that we don't yet understand? And if it was something, what was it? Where did it come from? And this is where the Big Bang theory starts to crack at the edges, because it doesn't have good answers to these questions. Now, there's another piece of the puzzle that's been bothering scientists for a while, and that's the composition of the universe. We know from observations that ordinary matter, the stuff that makes up stars, planets, and us, only accounts for about 5% of the universe. 5%. The rest is dark matter and dark energy, these mysterious components that we can't directly observe but we know exist because of their gravitational effects. Dark matter makes up about 27%, and dark energy, which is even more mysterious, makes up about 68%. So 95% of the universe is made up of stuff we don't understand. That's a pretty big gap in our knowledge, and it suggests that maybe, just maybe, we're missing something fundamental about how the universe works. But let's get back to the Big Bang itself. There's a concept in cosmology called the Planck time, which is 10 to the negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. It's the smallest unit of time that has any meaning in physics. Anything shorter than that and our current understanding of physics breaks down. We simply don't have the tools to describe what happens at that scale. But here's the thing, the Big Bang theory can only take us back to the Planck time. Before that, we're essentially in the dark. We don't know what happened in that first, incomprehensibly tiny fraction of a second. And that's a problem because if we don't understand that first moment, how can we be sure there wasn't something before it? This is where a theory called cosmic inflation comes in, and it's one of the most important modifications to the Big Bang theory that's been proposed. Inflation suggests that before the hot Big Bang we're familiar with, there was a period of exponential expansion where the universe grew by an absolutely staggering amount in an absurdly short time. We're talking about the universe doubling in size not once, not twice, but dozens of times in a fraction of a second. This would explain a lot of things that the standard Big Bang theory struggled with, like why the universe appears so uniform on large scales. But here's the kicker. Some physicists argue that from our perspective, cosmic inflation is the Big Bang. It's the explosion that started it all, which means the traditional Big Bang, the one we've been talking about this whole time, might not be the actual beginning. It might just be what happened after the beginning. And if inflation happened before the Big Bang, what caused inflation? Where did the energy for that exponential expansion come from? Some theories suggest it came from the energy inherent in space itself, from quantum fields that existed in some kind of pre-inflationary state. But that means there was a state before the Big Bang, a pre-existing condition, something that was already there before the universe as we know it began. And if something was there before, then the Big Bang wasn't the beginning. It was just a transition, a phase change, from one state to another. This is where my brain starts to hurt, and I imagine yours does too. Because if the Big Bang wasn't the beginning, then what was? How far back does this go? Is there an ultimate beginning, or does it just keep going backwards forever? Are we dealing with some kind of cyclical universe that goes through endless cycles of expansion and contraction? Or is there a multiverse where our universe is just one bubble in an infinite foam of universes, each with their own Big Bangs, their own histories, their own physical laws? The more we learn, the more questions we have, and that's both exciting and terrifying, because every answer we find seems to open up 10 new questions. And some of those questions are starting to suggest that maybe, just maybe, there are things that existed before the Big Bang, things that shouldn't be possible according to our current understanding, things that challenge the very notion that the universe had a beginning at all. Now, I know what some of you are thinking. This is all very theoretical. This is physicists and cosmologists playing with equations and models. Where's the actual evidence? Where are the observations? And that's a fair question. But here's the thing, we're starting to find evidence, real, tangible, physical evidence that suggests there might have been something before the Big Bang, evidence that's been staring us in the face this whole time, but we didn't know how to interpret it. Evidence that's forcing us to reconsider everything we thought we knew about the origin of the universe. We're finding anomalies in the cosmic microwave background that don't quite fit the standard model. There are structures in the universe that seem too large and too old to have formed in the time available since the Big Bang. There are patterns in the distribution of galaxies that hint at influences from beyond our observable universe. And then there are things here on Earth, ancient things, geological formations and archaeological sites that seem to tell a story that predates what should be possible. We're going to dive into all of this in the coming chapters. We're going to look at crystals that remember events from before they should have existed. We're going to explore the possibility that advanced civilizations might have existed long before the current epoch of the universe. We're going to examine the scars left on our planet by cataclysmic events that reshaped reality itself. And we're going to confront the deeply unsettling possibility that when the universe began, whenever and however that actually happened, it wasn't starting from nothing. Something was already there, waiting. The Big Bang might be the greatest story ever told about the origin of the universe, but like all great stories, it's incomplete. And the missing chapters, the ones we're just starting to uncover, might be the most important ones of all, because they don't just tell us where we came from, they tell us what was here before we were. And that changes everything. Echoes in deep time, Zircon's impossible tale. So we've established that the Big Bang might not be the beginning we thought it was, that maybe, just maybe, there was something before. But that's all very theoretical, right? That's physicists sitting in their offices, scribbling equations on whiteboards and arguing about quantum foam and inflation fields. What we need is actual evidence, real, tangible, physical proof that something existed before it should have. And here's the thing that absolutely blows my mind. We've had that evidence sitting in labs for decades. We just didn't realize what we were looking at. Enter the zircon crystal. Now, I know what you're thinking. A crystal? We're talking about the origins of the universe, and you're going to tell me about some rock? But trust me, these aren't just any rocks. Zircons are quite possibly the most important geological samples we've ever discovered. They're time capsules. Microscopic witnesses to events that happened so long ago that our brains can barely process the timescales involved, and the story they tell is absolutely impossible, or at least it should be. Let me give you some context here because this is crucial. Earth formed about 4.56 billion years ago. We know this from dating meteorites, which are essentially leftover building blocks from the formation of our solar system. Now, the earliest period of Earth's history is called the Hadean Eon, and it's named after Hades, the Greek underworld, because scientists assumed it was a hellish landscape of molten rock, constant asteroid bombardment, and absolutely nothing that could support life. The Hadean lasted from Earth's formation until about 4 billion years ago. For decades, the assumption was that Earth during this time was basically a ball of lava, inhospitable, violent, a place where nothing complex could survive, let alone form. The problem with studying the Hadean is that we don't have rocks from that time, or at least we didn't think we did. See, Earth is geologically active. Plate tectonics constantly recycle the crust. Old rocks get subducted into the mantle, melted down and reformed. The oldest intact rock formations we've found are only about 4.02 billion years old. That leaves a gap of over 500 million years where we have basically no direct evidence of what Earth was like. It's like trying to understand the entire history of human civilization, but you're missing the first several thousand years. You can make educated guesses, but you're essentially working blind. This is where zircon comes in and changes everything. Zircon is a mineral, zirconium silicate if you want to get technical, and it has some absolutely remarkable properties that make it invaluable to geologists. First, it's incredibly hard and resistant to weathering. While other minerals break down over time, zircon just keeps on trucking. It can survive being eroded out of one rock, transported by rivers, and then incorporated into a completely new rock formation. It's the geological equivalent of a Nokia phone. You just can't kill it. Second, and this is the really important part, zircon crystals incorporate uranium into their structure when they form, but they exclude lead. This is crucial because uranium decays into lead at a very predictable rate. We're talking about a half-life of 4.47 billion years for uranium-238. So when you find lead inside a zircon crystal, you know it came from uranium decay, and you can use the ratio of uranium to lead to calculate exactly when that crystal formed. It's like having a built-in clock that's been running since the moment the crystal solidified. Now here's where it gets interesting. In the early 1990s, geologists were working in a remote region of Western Australia called the Jack Hills. They were examining sandstone formations that were about 3 billion years old, which is already ancient by any standard. But when they looked closer at these rocks, they found something extraordinary. Embedded in the sandstone were tiny zircon crystals that were much, much older than the rock itself. These zircons had been eroded out of even more ancient rocks that no longer exist, transported by ancient rivers, and then cemented into this younger sandstone. When they dated these zircons using uranium-lead dating, they found crystals that were over 4 billion years old. And then they found one that was 4.404 billion years old. Let me put that in perspective. This crystal formed just 160 million years after Earth itself came into existence. The gap between the formation of Earth and the formation of this crystal is shorter than the gap between the extinction of the dinosaurs and today. This thing has been sitting around for 96% of Earth's entire history. It's older than any rock, any mountain range, any continent. It predates the oldest fossils by nearly 3 billion years. This tiny speck of mineral, smaller than a grain of sand, is the oldest thing we've ever found on Earth, and it shouldn't exist. According to everything we thought we knew about the early Earth, there shouldn't be any zircons from this time period because zircons form from cooling magma, specifically from granitic magma, which is associated with continental crust. And continental crust requires plate tectonics, which requires a cooled and solidified surface. But the Hadean Earth was supposed to be molten, a magma ocean. No solid crust, no continents, no conditions where zircon could form. So either our understanding of the Hadean was completely wrong, or these zircons are telling us something we're not ready to hear. Scientists being scientists, they immediately started analyzing the hell out of these crystals. And this is where things start to get really weird. Zircons don't just tell you when they formed, they also preserve chemical information about the conditions they formed in. One of the most important pieces of information comes from oxygen isotopes. Now, bear with me because this is going to sound technical, but it's actually not that complicated. Oxygen comes in different isotopes, mainly oxygen-16 and oxygen-18. The ratio between these two isotopes in a mineral tells you about the temperature and the presence of water when that mineral formed. Specifically, if a zircon has a high ratio of oxygen-18, that suggests it formed from magma that had interacted with water at relatively cool temperatures. When scientists analyzed the oxygen isotopes in these ancient zircons from Jack Hills, they found something that absolutely should not be there. The ratios indicated that these zircons formed from magma that had interacted with liquid water, on an Earth that was supposed to be a hellish ball of molten rock. The implications of this are staggering. Liquid water means temperatures below 100 degrees Celsius at the surface. It means a solid crust. It means an atmosphere. It means conditions that were potentially habitable. And all of this was happening just a few 100 million years after Earth formed, during a time we thought the planet was completely inhospitable. Now I can already hear the skeptics. And to be fair, the scientific community was skeptical too. Some argued that the oxygen isotope ratios could have been altered later by metamorphism or hydrothermal fluids, essentially resetting the clock, and that's a fair criticism. Zircons are tough, but they're not indestructible. If they get hot enough or exposed to the right fluids, their chemistry can be modified. So scientists went back and did more detailed analyses. They used techniques that could examine different parts of the crystal, because zircons grow in layers, like tree rings. The core of the crystal forms first, and then additional layers grow around it over time. By analyzing just the cores of these ancient zircons, where any later alteration would be minimal, they confirmed the results. The oxygen isotope signatures were original. These crystals really did form in the presence of water. But it gets even weirder. Some of these zircons show evidence of being recycled multiple times. They have cores that are extremely old, surrounded by rims that are slightly younger but still ancient. This suggests that even in the Hadean, there was a rock cycle happening. continental crust was forming, eroding, and being recycled. This is plate tectonics, or at least something very much like it, happening at a time when we thought Earth's surface was too hot and too unstable for such processes. In 2014, a team at Caltech published a study that analyzed rare earth elements and high-pressure signatures in zircons dating back 3.35 billion years. They found evidence that these zircons had been subjected to high pressures and low temperatures, conditions that are characteristic of subduction zones where one tectonic plate slides beneath another. This pushed the evidence for plate tectonics back to at least 3.35 billion years ago, much earlier than many scientists had believed possible. And if plate tectonics was operating then, it raises the question of how much earlier it might have started. Could it have been active during the Hadean? The zircon evidence certainly suggests it's possible. Then there's the question of oxidation. In 2016, researchers found zircons with rims that were 4.1 billion years old, and the chemistry of these rims indicated they formed in relatively oxidized conditions. This is bizarre because the early Earth's atmosphere was supposed to be reducing, meaning it had very little oxygen. Oxidized conditions suggest either that oxygen was being produced somehow, possibly by early photosynthetic life, or that the early Earth's atmosphere wasn't as reducing as we thought. Either way, it's a major deviation from the standard model. Now, let's step back for a second and think about what all of this means. We have crystals that are over 4 billion years old. They contain chemical signatures that tell us Earth had liquid water, a solid crust, possibly continents, and maybe even plate tectonics far earlier than we ever imagined. The Hadean, which we thought was a fiery hellscape, might have actually been relatively cool and wet for at least parts of its duration. Some scientists have even suggested that if conditions were this clement, life could have emerged much earlier than the oldest fossils suggest. We're talking about life possibly existing just a few 100 million years after Earth formed, and if life emerged that early, it could have been wiped out multiple times by the massive asteroid impacts that were still happening during the late Hadean. We could be the descendants of not the first attempt at life on Earth, but the second, third, or even 10th. But here's where my brain starts to really tie itself in knots. If these zircons are preserving evidence of conditions that shouldn't have existed according to our models, what else are they preserving? What other information is locked inside these crystals that we haven't figured out how to read yet? Because here's the thing about zircons, they're virtually indestructible. They survive everything. They outlast the rocks they formed in. They get recycled through Earth's crust multiple times. They witness events that would destroy any other mineral. They are, quite literally, the most enduring witnesses to Earth's history that we have. And this is where things start to get uncomfortable. We've established that the Big Bang might not be the beginning. We've established that our models of early Earth were wrong. But what if there's a connection between these two things that we're missing? What if the information preserved in these ancient zircons isn't just telling us about early Earth, but about something even older? I know that sounds insane. I know it sounds like I've completely lost the plot here. But hear me out. Zircons form from cooling magma. They incorporate elements from their environment. They preserve isotopic signatures that tell us about temperature, water, atmospheric composition. But they also incorporate trace elements, rare earth elements, isotopes of elements that have various decay pathways. And some of these decay pathways have half-lives that are comparable to or longer than the age of the universe itself. Uranium-238, for instance, has a half-life of 4.47 billion years. Thorium-232 has a half-life of 14 billion years. Samarium-147 has a half-life of 106 billion years, which is nearly 8 times the current age of the universe. Now, when we use these elements to date rocks, we're assuming that when the rock formed, it incorporated these elements at known ratios based on the composition of the solar nebula. We're assuming that the isotopic ratios we measure today are purely the result of radioactive decay since the rock formed. But what if that assumption is wrong? What if some of these isotopes, in some of these ancient zircons, are carrying signatures from before Earth formed, from before the solar system formed, from materials that were part of previous generations of stars or even previous cosmic cycles? We know that the matter that makes up Earth, including the uranium and thorium and other heavy elements in zircons, was created in supernova explosions of earlier generations of stars. The early universe, right after the Big Bang, only had hydrogen and helium. Everything heavier than that, all the carbon and oxygen and silicon and iron and uranium, was cooked up inside stars and then blasted out into space when those stars died. So every atom of uranium in these ancient zircons was once inside a star that exploded billions of years before Earth formed. That uranium carries a history that predates our planet, predates our sun, predates our solar system. But here's the really wild part. Some of these zircons contain xenon isotopes that have unusual ratios. Xenon is a noble gas, and it doesn't usually get incorporated into minerals because it doesn't react with anything. But zircons can trap tiny amounts of xenon in their crystal structure, and when scientists analyzed the xenon in some of these ancient zircons, they found isotopic anomalies, deviations from what you'd expect if all the xenon came from the solar nebula. Some of these anomalies suggest contributions from nucleosynthesis processes that happened in specific types of supernovae, or in neutron star mergers, or in other exotic astrophysical events. Essentially, these zircons are carrying fingerprints of the deaths of stars that existed before our sun was born. This is where I start to wonder if we're missing something big. These crystals are over 4 billion years old. They've survived everything Earth has thrown at them. They contain material that predates the solar system. They preserve chemical signatures that challenge our understanding of early Earth. And they're virtually indestructible, meaning they could, in theory, survive even more extreme conditions than anything Earth has experienced. Could a zircon survive a planetary collision? Could it survive being ejected into space and spending millions of years in the interstellar medium before being incorporated into a new planetary system? Could it survive conditions that predate the current cosmic epoch? I'm not saying these zircons are from before the Big Bang. That would be absurd. The Big Bang was 13.8 billion years ago, and these zircons are only 4.4 billion years old. There's a gap of over 9 billion years there. But what I am saying is that these crystals demonstrate that minerals can preserve information over timescales that approach the age of the universe. They can survive recycling through multiple geological processes. They can carry signatures from before the objects they're found in existed. And if that's true for zircons on Earth, what about zircons or similar minerals on other planets? On planets that are older than Earth? On planets orbiting stars that formed much earlier in the universe's history? We know that the first stars formed just a few 100 million years after the Big Bang. We know that some of those early stars were massive and short-lived, exploding as supernovae and enriching the interstellar medium with heavy elements. We know that second and third generation stars formed from that enriched material could have had rocky planets much earlier than our solar system. There could be planets out there that are 10 billion years old, twice the age of Earth. And if those planets had zircons, and if some cosmic event ejected those zircons into space, and if they eventually made their way into our solar system and got incorporated into Earth during its formation, we could have crystals on Earth that are older than Earth itself. Visitors from ancient worlds that existed when the universe was young. Now, before you click away thinking I've gone full tinfoil hat, let me be clear, we have no evidence that any of the zircons we've found are from outside the solar system. All of the isotopic signatures we've analyzed are consistent with them forming from material that was part of the solar nebula. But the point I'm trying to make is that the mere existence of these crystals, their durability, their ability to preserve information over billions of years, opens up possibilities that we haven't fully explored. It demonstrates that geological materials can be witnesses to deep time in ways we're only beginning to understand. And this brings us back to the central question of this video. If we're finding evidence that challenges our understanding of Earth's early history, if we're discovering that conditions were radically different than we thought, if we're learning that our models have been wrong, what else are we wrong about? What other assumptions are we making that are going to be overturned by the next discovery? Because here's the uncomfortable truth that scientists don't like to talk about. Every time we develop a new analytical technique, every time we build a better instrument, every time we figure out how to extract more information from these ancient samples, we find something that surprises us. We find evidence that doesn't fit the models. We find anomalies that take years or decades to explain. And sometimes we find things that we can't explain at all. These zircons are telling us a story, but we're only reading the first few pages. There are entire chapters locked inside these crystals that we don't yet have the tools to access. Information encoded in isotopic systems we haven't measured, in trace element distributions we haven't mapped, in crystal defects and inclusions we haven't analyzed. Every one of these tiny crystals is a library, and we've barely scratched the surface of what they contain. And that's what makes this so exciting and so terrifying at the same time. Because if these crystals can overturn our understanding of the Hadean, if they can demonstrate that Earth was habitable far earlier than we thought, if they can preserve signatures from before our solar system existed, what else might they reveal? What other impossible truths are hidden in plain sight, waiting for us to develop the tools to read them? The zircons from Jack Hills have already rewritten the history of early Earth. They've pushed back the timeline for liquid water, for a solid crust, for potentially habitable conditions. They've demonstrated that our models of planetary formation and early evolution were too simplistic. But I think they're trying to tell us something even more profound, something that connects to the larger questions about the Big Bang and what came before. They're showing us that information can be preserved across timescales we can barely comprehend, that the universe has a memory written in stone, in crystal, in the very atoms that make up these ancient minerals. And if the universe has a memory, if information can persist across billions of years, then maybe the question isn't whether something existed before the Big Bang, but whether we're looking in the right places for evidence of it. Because if that evidence exists, it won't be in telescope observations or particle collider experiments. It'll be in the deep time records preserved in the oldest materials we can find, in crystals that have witnessed epochs we can barely imagine, in minerals that carry secrets from before our world began. The zircons are whispering to us across 4 billion years. They're trying to tell us something important, and the more we listen, the more unsettling their message becomes. Because they're not just saying that our models of early Earth were wrong. They're suggesting that everything we think we know about origins, about beginnings, about where we came from, might need to be reconsidered. And that's just from studying rocks on our own planet. Now imagine what we might find when we start seriously looking for these kinds of records elsewhere. On Mars, which has even older surface rocks. On asteroids that have never been geologically active and might preserve materials from the earliest days of the solar system. On exoplanets orbiting ancient stars, the universe is full of deep time witnesses. We've only just started listening to what they have to say, and if the zircons are any indication, The story they're going to tell us is going to be far stranger than we ever imagined. Strange enough that we might have to confront the possibility that Earth's history, and perhaps even cosmic history, includes chapters that predate what we thought was the beginning. But zircons are just rocks. They can tell us about geology, about chemistry, about the physical conditions of the early Earth. What they can't tell us is whether anyone was here to witness it, whether intelligence of any kind existed before the current epoch of life on Earth. And that's a question that takes us into even more controversial territory. Because if the timeline of Earth's history is longer and more complex than we thought, if conditions were habitable much earlier, then we have to ask a deeply uncomfortable question: could something have been here before us? Could there have been a previous chapter of history, not just geological history, but the history of life, of civilization, of intelligence, a chapter that's been erased so thoroughly that we're only now finding the faintest hints that it ever existed at all? The Silurian Hypothesis, ghosts of pre-cosmic civilizations. So we've talked about how the Big Bang might not actually be the beginning, and we've explored how ancient zircon crystals are rewriting our understanding of Earth's early history, proving that conditions were habitable far earlier than we ever imagined. But now we need to ask an even more uncomfortable question, one that's going to sound absolutely insane until you actually sit down and think about it. If Earth had liquid water and potentially habitable conditions just a few 100 million years after it formed, and if the geological record is as incomplete as we know it is, could something have been here before us? Not just life, but intelligent life. A civilization that rose, flourished, and vanished so long ago that we've only just started to realize we should even be looking for evidence of it? This is where we enter the territory of the Silurian Hypothesis, and I need to be very clear right from the start about what this is and what it isn't. This is not some fringe conspiracy theory cooked up by ancient alien enthusiasts or people who think lizard people run the government. The Silurian Hypothesis is a legitimate scientific thought experiment published in 2018 in the International Journal of Astrobiology by two very credible scientists, Gavin Schmidt, a climatologist at NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester. These are serious people asking a serious question. If an industrial civilization existed on Earth millions of years ago, would we even be able to tell? Now, the name comes from a 1970 episode of Doctor Who called Doctor Who and the Silurians, where these reptilian humanoids had supposedly been hibernating for 400 million years and woke up because of nuclear testing or something. It's a fun sci-fi premise, but here's the thing. The actual Silurian period was 443 to 419 million years ago, and there was barely any complex life on land at that point, let alone intelligent reptiles building nuclear reactors. So the name is deliberately tongue-in-cheek, a nod to the absurdity of the idea, while simultaneously asking whether the absurd might actually be worth investigating. The hypothesis emerged from a simple question posed to Schmidt by a reader. If an advanced civilization lived on Earth millions of years ago, would we be able to tell? And instead of dismissing it outright, Schmidt and Frank actually sat down and worked through the math and the geology. And what they found was deeply unsettling. The answer isn't a simple yes or no. It's more like maybe, but probably not. And here's why that should terrify you. Let's start with some uncomfortable facts about the geological record. Humans have been around for about 300,000 years. Modern industrial civilization has existed for maybe 300 years, depending on how you count it. That's a blink of an eye in geological terms. The Earth is 4.56 billion years old. Complex life has existed for maybe 600 million years. The amount of time we've been doing anything that would leave a detectable trace in the rock record is so infinitesimally small that it barely registers. We're talking about 0.0000066% of Earth's history. It's nothing. Now here's the really uncomfortable part. The geological record is not complete. It's not even close to complete. Plate tectonics are constantly recycling Earth's crust. Old ocean floor gets subducted into the mantle at rates of a few centimeters per year, which doesn't sound like much, but over millions of years it adds up. The oldest ocean floor we have is only about 200 million years old. Everything older than that has been recycled, gone, melted back into the mantle and reformed into new crust. Continental crust lasts longer because it's less dense and doesn't get subducted as easily, but even continents aren't permanent. They get eroded, broken apart, reassembled. The rock record for any given location is full of gaps, unconformities, periods where either no rocks were deposited or the rocks that were there got eroded away or metamorphosed beyond recognition. Schmidt and Frank calculated that over 100 to 200 million years, plate tectonics will recycle about 99% of the Earth's crust. That means if there was an industrial civilization on Earth 100 million years ago, 99% of the direct physical evidence, the cities, the roads, the factories, all of it would be gone. Subducted, melted, recycled. What would be left would be indirect traces, chemical signatures, isotopic anomalies, things that might be preserved in the small fraction of rock that survives long enough for us to find and study it. So what would those traces look like? Well, we can actually answer this question pretty well because we're currently creating them. Industrial civilization is leaving a very distinct signature on the planet. We've dramatically altered the carbon cycle by burning fossil fuels, releasing carbon dioxide that's been locked underground for hundreds of millions of years. This carbon has a distinct isotopic signature. It's depleted in carbon-13 compared to carbon-12 because plants preferentially take up carbon-12 during photosynthesis, and fossil fuels are made from ancient plants. When we burn those fuels, we're releasing carbon with that distinctive isotopic signature into the atmosphere and oceans. We're also depositing plastics everywhere, and plastics don't biodegrade, they just break down into smaller and smaller pieces. Microplastics are now found in sediments all over the world, in the deepest ocean trenches, in Arctic ice cores, everywhere. We're mining and refining metals at industrial scales, creating concentrations of heavy metals like lead, cadmium, and mercury that don't occur naturally. We're producing synthetic chemicals like PCBs and forever chemicals that have never existed in Earth's history. We've detonated nuclear weapons, leaving traces of radioactive isotopes like plutonium-239 and carbon-14 that have very specific signatures and wouldn't exist naturally. And we're causing a mass extinction, driving species to extinction at rates that haven't been seen since the dinosaurs died out 66 million years ago. All of this will leave traces in the geological record. The question is, how long will those traces last? And would we recognize them if they were millions of years old? The plastic will eventually break down into carbon and other elements, but the chemical signatures might persist in certain types of sediments. The isotopic anomalies from fossil fuel burning will show up as a spike in carbon isotope ratios in sedimentary rocks. The heavy metal concentrations will be preserved in certain types of deposits. The radioactive isotopes will decay, but they'll leave daughter products that might be detectable. The mass extinction will show up as a dramatic decrease in biodiversity in the fossil record. But here's the problem. All of these signals are subtle. They require very specific types of preservation and very careful analysis to detect, and they all fade with time. After a few million years, many of these signals would be hard to distinguish from natural variations. After tens of millions of years, most of them would be gone or so degraded that you'd need to know exactly what you were looking for to find them. And after 100 million years, with 99% of the crust recycled, you'd be lucky to find anything at all. Schmidt and Frank point to an event in Earth's past that might be a good analog for what an ancient industrial civilization would look like in the geological record. It's called the Paleocene-Eocene Thermal Maximum, or PTM for short, and it happened about 56 million years ago. During the PTM, global temperatures spiked by 5 to 8 degrees Celsius over the course of a few thousand years. This was accompanied by a massive release of carbon into the atmosphere. We're talking about thousands of gigatons, which caused ocean acidification and a major extinction event in marine ecosystems. The carbon isotope ratios in sediments from this time show the exact same kind of depletion in carbon-13 that we're seeing today from burning fossil fuels. Now, scientists have a pretty good explanation for the PETM that doesn't involve ancient civilizations. It was most likely caused by a massive release of methane from ocean sediments, possibly triggered by volcanic activity or an asteroid impact. The methane oxidized to carbon dioxide in the atmosphere, causing the warming and the isotopic anomaly. But here's the thing: if you didn't know about the methane explanation, if you just looked at the carbon isotope data, you could make a case that it looks like what an industrial civilization would produce: a sudden, massive input of carbon with a depleted isotopic signature. It's not proof of anything, but it demonstrates that the geological record can preserve these kinds of signals over tens of millions of years. And this is where the Silurian hypothesis gets really uncomfortable. Because if we found another event like the PETM, another carbon isotope anomaly, another spike in heavy metals, another sudden extinction event, how would we know whether it was natural or artificial? How would we distinguish between a massive volcanic event and the industrial activity of a long-vanished civilization? The answer is, we probably couldn't, not without a lot more evidence. And that evidence might not exist anymore. Schmidt and Frank are very careful to point out that they're not claiming there actually was an ancient industrial civilization on Earth. They explicitly say care must be taken not to postulate such a cause until actually positive evidence is available. What they're doing is asking what that positive evidence would look like and whether we'd even recognize it if we found it. And they're also making a broader point about astrobiology and the search for extraterrestrial intelligence. If we can't reliably detect the traces of an industrial civilization in our own planet's geological record after 100 million years, how are we going to detect ancient civilizations on other planets? What should we be looking for? This connects back to something called the Fermi paradox, which is the question of why, if the universe is so old and so big and presumably full of potentially habitable planets, we haven't detected any signs of alien civilizations. One possible answer is that civilizations don't last very long. They might burn through their resources, destroy their environment, or wipe themselves out with weapons of mass destruction. If the average industrial civilization only lasts a few thousand years before collapsing, then the odds of two civilizations existing at the same time in a way that they could detect each other become vanishingly small. Frank and one of his colleagues, Woodruff Sullivan, published a paper in 2016 calculating that for us to be the only civilization that has ever existed in the observable universe, the probability of a habitable planet developing a technological civilization would have to be less than 1 in 10 billion trillion. That's 10 to the negative 22. That's such an absurdly small number that it's almost certainly not true, which means there almost certainly have been other civilizations out there. We just haven't detected them because they're gone, and they've been gone for so long that their signals have faded into the cosmic background noise. And this is where the Silurian hypothesis ties into the larger theme of this video. If civilizations can rise and fall and leave barely any trace after 100 million years, what about 1 billion years? What about 10 billion years? What about timescales that approach the age of the universe itself? Because the universe is 13.8 billion years old, and the first stars formed just a few 100 million years after the Big Bang. Those early stars were massive and short-lived, but they enriched the interstellar medium with heavy elements. Second and third generation stars, formed from that enriched material, could have had rocky planets much earlier in the universe's history. There could have been planets with life, with intelligent life, with technological civilizations, billions of years before Earth even existed. And here's the deeply uncomfortable thought. If those civilizations existed, and if they lasted for any significant amount of time, what did they learn? What did they discover? Did they figure out the nature of dark matter and dark energy? Did they learn to manipulate space-time, to create wormholes, to travel between galaxies? Did they find a way to survive the heat death of the universe, or to escape into other dimensions, or to seed new universes with the conditions necessary for life? And if they did, would we even recognize the traces of their existence? Would we be able to tell the difference between a natural phenomenon and an artifact of technology so advanced it might as well be magic? Arthur the 100th. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic, but I think there's a corollary to that. Any sufficiently ancient technology is indistinguishable from nature. If you go back far enough, if the timescales are long enough, even the most massive engineering projects would erode, decay, and be recycled by natural processes. Stars would be born and die in the ruins of ancient megastructures. Planets would form from the dust of disassembled worlds. The universe itself would forget that anything artificial had ever existed, and all that would remain would be subtle anomalies, things that don't quite fit the models, things that make you wonder if maybe, just maybe, someone was here before. Adam Frank said in an interview with Popular Mechanics, "With the Silurian hypothesis, we articulated the kinds of signals that our civilization would leave if we disappear and somebody looks for our civilization 10 or 20 million years from now. But I think the implications go much deeper than that. Because if our civilization, with all our concrete and steel and plastic and nuclear waste, would be nearly undetectable after 100 million years, what does that say about the possibility of detecting civilizations that existed billions of years ago? Civilizations that might have been far more advanced than us, that might have learned to minimize their environmental footprint, that might have achieved true sustainability. Gavin Schmidt raised this point himself. The more sustainable a civilization is, the smaller its geophysical footprint might be. What does that imply for the detectability of long-term civilizations? It's a fascinating question because it flips the usual assumption on its head. We tend to think that more advanced civilizations would leave bigger, more obvious traces. But what if the opposite is true? What if the most advanced civilizations are the ones that learn to exist in perfect harmony with their environment, leaving no trace at all? What if the reason we don't see evidence of ancient civilizations isn't because they didn't exist, but because they were too good at what they did? Now, let's bring this back to Earth and the actual geological evidence. We've talked about the PETM as a possible analog for what an industrial civilization might look like in the deep time record, but there are other events in Earth's history that raise questions. There are periods of rapid climate change, sudden spikes in atmospheric carbon dioxide, mass extinctions that don't have clear causes. Most of these have perfectly good natural explanations involving volcanism, asteroid impacts, changes in ocean circulation, or shifts in the carbon cycle. But the Silurian hypothesis forces us to ask, how would we know? How would we distinguish between a natural event and an artificial one if the artificial event happened 100 million years ago and 99% of the evidence has been recycled? The answer is that we'd need to look for very specific technosignatures, markers that couldn't be produced by natural processes. Things like anomalous concentrations of synthetic elements, isotopic ratios that don't match any known natural process, microstructures in rocks that show signs of artificial manufacturing, or patterns in sedimentation that indicate deliberate engineering. We'd need to find multiple lines of evidence that all point in the same direction. And we'd need to rule out every possible natural explanation before we could even begin to consider an artificial one. And here's the thing, we're not really looking. The geological community isn't systematically searching for signs of ancient industrial civilizations because, frankly, it sounds ridiculous. The prior probability is assumed to be so low that it's not worth the effort. But Schmidt and Frank's point is that maybe it should be worth the effort, not because we expect to find anything, but because the act of looking, the act of defining what we'd expect to see, refines our understanding of what's natural and what's not. It helps us calibrate our models of Earth's systems, and it prepares us for the day when we start examining the geological records of other planets, where the question of ancient civilizations might be much more relevant. Mars, for instance, is geologically dead. It doesn't have plate tectonics. Its surface is incredibly old in many places, preserving features that are billions of years old. If there had been a civilization on Mars, or if Mars had been visited by a civilization from elsewhere, the evidence might still be there, waiting to be found. We've barely scratched the surface of Mars, literally. We've examined a tiny fraction of the planet in any detail. What might be hiding in places we haven't looked yet? And this brings us full circle to the question of the Big Bang and what came before. Because if the Silurian hypothesis teaches us anything, it's that absence of evidence is not evidence of absence, especially when you're dealing with timescales that are almost incomprehensible. The fact that we haven't found signs of ancient civilizations on Earth doesn't mean they didn't exist. It just means that if they did exist, they existed so long ago that the evidence has been erased by natural processes, or it's so subtle that we haven't figured out how to recognize it yet. Now, applying this logic to the question of pre-Big Bang civilizations is obviously a massive leap. We're talking about timescales that are even more extreme, conditions that are completely alien to anything we can study directly. But the principle is the same. If something existed before the Big Bang, before the current epoch of the universe, what traces would it leave, and would we even know where to look? Some physicists have speculated about structures in the cosmic microwave background that might be echoes of events from before the Big Bang, regions where the quantum fluctuations that seeded the formation of galaxies might have been influenced by pre-existing conditions. Others have looked at anomalies in the large-scale structure of the universe, the distribution of galaxies and galaxy clusters, searching for patterns that might indicate the universe isn't quite as homogeneous as the standard model predicts. These are subtle things, statistical anomalies, things that might be explained by natural processes we don't fully understand yet, or might be hints of something more. The Silurian hypothesis, at its core, is about humility. It's about recognizing the limits of what we can know, about understanding that our perspective is constrained by the tools we have and the assumptions we make. It's a reminder that the universe is far older and far stranger than we often give it credit for, and that the absence of obvious evidence for something doesn't mean that something didn't happen. It just means we need to look harder, think more carefully, and be willing to question our assumptions. So could there have been a civilization on Earth before us, one that rose and fell so long ago that we're only now starting to realize we should even be asking the question? The honest answer is probably not. The evidence just isn't there, and the prior probability is really low. But the fact that we can't rule it out definitively, the fact that the geological record is incomplete enough that such a thing could have happened and we might not know, that's what makes the Silurian hypothesis so valuable. It forces us to confront the limits of our knowledge and the biases in our thinking, and it sets the stage for the next uncomfortable question. If the geological record is this incomplete, if so much of Earth's history has been erased or obscured, what about the events we do have evidence for? What about the massive impacts, the volcanic eruptions, the climate catastrophes that we know happened? Because Earth's surface is scarred, deeply scarred, by violence on scales we can barely comprehend. And some of those scars tell stories that don't quite make sense. Stories of events so extreme that they challenge our understanding of what's possible. Stories that might, just might, be connected to something that predates not just human civilization, but the current configuration of the cosmos itself. And that's where we're going next. Planetary scars. Earth's violent memory. So we've established that ancient civilizations could have existed on Earth and left almost no trace, that the geological record is so incomplete and so heavily recycled that entire epochs of history could be hidden from us. But here's the thing that really keeps me up at night. We don't need to speculate about hypothetical ancient civilizations to understand how thoroughly Earth can erase its own history. We have direct evidence of catastrophic events that reshaped the planet so dramatically, so violently, that they essentially hit the reset button on life as it existed at the time. Events that happened so quickly that if you weren't paying attention, you'd miss the transition entirely. Events that make you wonder if what we think of as the history of life on Earth is really just the most recent chapter in a much longer, much stranger story. We're going to talk about two events in particular that demonstrate just how fragile the geological record really is, how quickly everything can change, and how a planetary trauma can make it look like the world is beginning anew when in reality it's just continuing under radically different conditions. The first is called the Paleocene-Eocene thermal maximum, and the second is the Younger Dryas Impact hypothesis. And both of these events are going to fundamentally challenge your understanding of how stable Earth's climate and biosphere actually are. Let's start with the Paleocene-Eocene thermal maximum, which scientists usually just call the PETM because nobody wants to say that mouthful every time. This event happened about 55.5 million years ago, give or take a few 100,000 years, which in geological terms is basically yesterday. To put that in perspective, this was about 9 million years after the dinosaurs went extinct, during a time when mammals were really starting to diversify and take over the ecological niches that the dinosaurs had left empty. The world was already pretty warm compared to today. There were palm trees growing in Wyoming, crocodiles living in the Arctic, and no permanent ice at either pole. It was a greenhouse world, the kind of climate that would make our current concerns about global warming look like a minor inconvenience. And then, over a period of somewhere between 10,000 and 20,000 years, which sounds like a long time but is actually incredibly rapid in geological terms, the global temperature spiked by 5 to 8 degrees Celsius. Let me put that in perspective for you. The difference between the last ice age, when glaciers covered most of North America and Europe, and today is only about 5 degrees Celsius. So we're talking about a temperature increase equivalent to the entire transition from an ice age to the modern climate, except it happened in a fraction of the time, and it was happening on top of a world that was already much warmer than today. The rate of warming during the PETM was somewhere between 0.025 and 0.4 degrees Celsius per century. depending on which studies you look at and how you interpret the data. Now, you might be thinking that doesn't sound too bad, right? That's pretty gradual. But here's the terrifying part. We're currently warming at about 1.1 degrees Celsius per century, which is at least twice as fast as the PETM, possibly up to 40 times faster. We are living through a climate change event that is more rapid than one of the most extreme natural climate shifts in Earth's history. Just let that sink in for a second. So what caused the PETM? Well, that's where things get complicated and honestly pretty contentious in the scientific community. The most widely accepted explanation involves a massive release of carbon into the atmosphere, somewhere between 3,000 and 7,000 gigatons of carbon. To put that in context, humans have released about 650 gigatons of carbon since the Industrial Revolution began. So we're talking about roughly 5 to 10 times the total amount of carbon we've released over the past 300 years, except it all got dumped into the atmosphere in maybe 10,000 years. That's an enormous amount of carbon released very quickly. But where did all this carbon come from? There are a few competing theories. The leading one involves something called the North Atlantic Igneous Province, which is a fancy way of saying there was massive volcanic activity happening where the North Atlantic Ocean is today. We're not talking about a single volcano here. We're talking about a region the size of several European countries where magma was pushing up through the Earth's crust, creating vast fields of volcanic rock. This kind of activity can release huge amounts of carbon dioxide directly into the atmosphere, but it can also do something even more dramatic. It can heat up the ocean floor, and this is where the other major theory comes in. The ocean floor, particularly in the Arctic and around the continental margins, contains massive deposits of something called methane hydrates. These are basically methane molecules trapped in a cage of ice, and they're only stable under very specific conditions of high pressure and low temperature. If you heat up the ocean floor, either through volcanic activity or through warming ocean currents, these methane hydrates become unstable and they release their methane into the ocean. Methane is a greenhouse gas that's about 25 times more potent than carbon dioxide over a century-long timescale. So if you release enough methane, it causes warming, which causes more methane release, which causes more warming. It's a runaway feedback loop, and it's absolutely terrifying. The evidence suggests that something like this probably happened during the PETM. We see massive carbon isotope anomalies in sediments from this time, specifically a 4 to 6 per mil negative shift in carbon-13. Now, I know that sounds incredibly technical, but what it means is that the carbon being released had a very specific isotopic signature that's consistent with either methane from hydrates or carbon from organic material like plants or fossil fuels. It's the same kind of signature we're seeing today from burning coal and oil, which is one of the reasons why climate scientists point to the PETM as a potential analog for what we're doing to the planet right now. And the impacts of the PETM were absolutely devastating. The oceans became acidified because all that carbon dioxide dissolves in seawater and forms carbonic acid. This caused massive die-offs of organisms that build their shells out of calcium carbonate, like foraminifera, which are these tiny single-celled organisms that live in the ocean. In the deep sea, somewhere between 30 and 50% of benthic foraminifera species went extinct. Their shells literally dissolved in the acidified water. We can see this in sediment cores, where there's a layer of what's called the carbonate compensation depth shift. Below a certain depth, there are no carbonate shells at all. They just dissolved. On land, the warming caused massive changes in ecosystems. The tropics became so hot that they may have become uninhabitable for many species. Equatorial ocean temperatures reached 36 degrees Celsius, which is close to the upper limit for most marine life. Forests expanded into polar regions. Rainfall patterns shifted dramatically, causing droughts in some areas and floods in others. And mammals, which had been diversifying and getting larger after the extinction of the dinosaurs, suddenly got smaller. This is called the Lilliput effect, and we see it clearly in the fossil record. Early horses, for example, which were already pretty small, shrank by about 30% during the PETM. Early whales and other marine mammals shrank by about 25%. This is probably because smaller body sizes are advantageous in hot climates. They allow for better heat dissipation, and also because the available food resources change dramatically. But here's what really gets me about the PETM. The biosphere recovered. It took about 150,000 to 200,000 years for temperatures to come back down and for the carbon cycle to restabilize, but it did happen. The excess carbon got absorbed by weathering of rocks, by increased plant growth, by burial in ocean sediments. The oceans recovered their chemistry. New species evolved to fill the niches left by the ones that went extinct. If you look at the fossil record a few million years after the PETM, you'd have no idea that anything catastrophic had happened. The planet moved on, and this is the point I want to emphasize here. Earth has a remarkable ability to reset itself, to erase the evidence of catastrophic events given enough time. The PETM was one of the most extreme climate change events in the past 100 million years, and yet if we didn't have very specific types of sediment cores from very specific locations, we might not even know it happened. The rock record from this time is spotty. There are huge gaps. Many of the sediments that were deposited during the PETM have been eroded away or buried under younger sediments or altered by metamorphism. The only reason we know about it in such detail is because paleoclimatologists have spent decades carefully extracting and analyzing cores from the deep ocean floor, where sedimentation is continuous and preservation is good. James Zachas, who's one of the leading researchers on the PETM at UC Santa Cruz, has said, "The PETM was a dress rehearsal for what we're doing now." And he's not wrong. But I think there's a deeper implication here that doesn't get talked about enough. If an event as extreme as the PETM can be almost invisible in the rock record unless you know exactly where to look and what to look for, what other events might have happened that we've completely missed? How many times has Earth hit the reset button that we don't know about? Which brings us to our second planetary scar, and this one is way more recent and way more controversial. It's called the Younger Dryas, and it's tied to a hypothesis that has been tearing the archaeological and geological communities apart for the past 20 years. The Younger Dryas Impact hypothesis suggests that about 12,900 years ago, right at the end of the last ice age, Earth was hit by a cosmic impact event that triggered a sudden and dramatic return to Ice Age conditions, caused the extinction of most of North America's megafauna, and potentially wiped out early human civilizations that were just starting to develop complex societies. Now, before we get into the evidence, let me give you some context on what the Younger Dryas actually was. At the end of the last ice age, about 15,000 years ago, the planet was warming up. The massive ice sheets that covered North America and Europe were melting, sea levels were rising, and the climate was becoming more hospitable. Animals and humans were moving into areas that had been locked under ice for millennia. And then, around 12,900 years ago, everything suddenly reversed. Temperatures in the northern hemisphere dropped by 2 to 6 degrees Celsius within the span of just a few decades. I want you to really think about that. Not centuries, not millennia. Decades. In some ice core records from Greenland, we can see temperature drops happening over a period as short as 10 years. This sudden cooling lasted for about 1,200 years, which is why it's called the Younger Dryas. It's named after a flower called Dryas octopetala, which is a cold-adapted plant that suddenly shows up in pollen records from this time in areas where it hadn't been present before. The climate in Europe and North America went from warming and relatively stable to cold and dry almost overnight in geological terms. Glaciers that had been retreating started advancing again, lakes that had been full dried up, and then, just as suddenly as it started, it ended. Around 11,700 years ago, temperatures shot back up, the ice sheets resumed their retreat, and the world entered the warm, stable climate of the Holocene epoch, which is the period we're still in today. The mainstream explanation for the Younger Dryas, the one you'll find in most textbooks, involves something called the Atlantic Meridional Overturning Circulation, or AMOC, which is the system of ocean currents that includes the Gulf Stream. The idea is that as the North American ice sheets melted, they released enormous amounts of fresh water into the North Atlantic. This fresh water, being less dense than salt water, formed a cap on the surface of the ocean that disrupted the normal circulation patterns. The Gulf Stream, which normally brings warm water from the tropics up to the North Atlantic, was shut down or severely weakened. Without that heat transfer, temperatures in the Northern Hemisphere plummeted. This is a perfectly reasonable explanation, and there's a lot of evidence to support it. We can see the meltwater pulse in sediment records. We can see changes in ocean circulation patterns. It all makes sense. Except there's a growing body of evidence that suggests something else happened as well, something that triggered the meltwater pulse in the first place, something from space. In 2007, a team of researchers led by Richard Firestone published a paper proposing that the Younger Dryas was triggered by a cosmic impact event. Not a single large asteroid like the one that killed the dinosaurs, but a fragmented comet or asteroid that airburst or impacted in multiple locations across the Northern Hemisphere. The evidence they presented was striking. At dozens of sites across North America, Europe and Asia, in a sediment layer that dates to exactly 12,900 years ago, they found unusual materials that shouldn't be there. These materials include nanodiamonds, which are microscopic diamonds that can form under conditions of extreme pressure and temperature, like during an impact or an explosion. They found magnetic microspherules, tiny spherical particles of iron that show evidence of having been melted at temperatures above 1,000 degrees Celsius. They found iridium and platinum anomalies, elevated concentrations of these rare elements that are more common in asteroids and comets than in Earth's crust. They found shocked quartz crystals with distinctive fracture patterns that only form under the extreme pressures of an impact. And they found a black matte layer, a carbon-rich layer full of charcoal and burned biomass that's consistent with massive wildfires. The hypothesis is that a comet or asteroid, probably several hundred meters across, broke apart as it entered the atmosphere and exploded in multiple airbursts over the Laurentide ice sheet, which covered most of Canada and the northern United States at the time. The energy released would have been equivalent to thousands of nuclear weapons going off simultaneously. The heat would have instantly melted massive amounts of ice, creating the meltwater pulse that disrupted ocean circulation. The shock waves would have triggered earthquakes and volcanic eruptions. The debris thrown into the atmosphere would have blocked sunlight, causing a nuclear winter effect that reinforced the cooling. And the fires ignited by the airbursts would have consumed about 10% of Earth's forests, releasing vast amounts of smoke and soot into the atmosphere. James Kennett, a geologist at UC Santa Barbara and one of the leading proponents of the Younger Dryas Impact hypothesis, has said, "The evidence for an impact is overwhelming." And you know what? When you look at the sheer volume of data that's been collected over the past 15 years, it's hard to argue with him. The markers are found at over 50 sites across 3 continents. They're all in the same stratigraphic layer. They all date to the same time. The probability of all of these anomalies occurring naturally and simultaneously is astronomically small. But, and this is a big but, the hypothesis is still controversial. The main criticism is that there's no crater. If there was an impact large enough to cause all of these effects, where's the smoking gun? Where's the impact structure? The proponents argue that the impact or impacts happened on the ice sheet, which was 2 miles thick in some places, and that the crater would have been in ice, not rock. When the ice sheet melted over the next few thousand years, any crater would have been erased. They also argue that most of the energy was released in airbursts, similar to the Tunguska event in 1908, which flattened 2,000 square kilometers of Siberian forest but left no crater. Other critics have argued that some of the evidence can be explained by natural processes. Nanodiamonds can form in forest fires under certain conditions. Microspherules can be produced by volcanic eruptions or cosmic dust that's constantly raining down on Earth. The platinum and iridium anomalies might be from volcanic activity. The black matte layer could just be from wildfires triggered by lightning or human activity. Every piece of evidence taken individually has alternative explanations. But here's the thing that the critics have a harder time explaining. In 2013, a team of researchers found a platinum anomaly in Greenland ice cores that dates to exactly 12,800 years ago. Platinum, like iridium, is much more abundant in asteroids and comets than in Earth's crust. The spike in platinum concentration is sharp and well defined, and it's found in multiple ice core records. Then in 2023, another study confirmed this platinum anomaly and found similar spikes at other sites around the world. The researchers concluded that the most likely explanation is extraterrestrial material depositing on Earth's surface during a short-lived event. And then there's the megafauna extinction. At the end of the Pleistocene, North America lost about 35 genera of large mammals. Mammoths, mastodons, saber-toothed cats, giant ground sloths, camels, horses, dire wolves, short-faced bears, all gone within a span of maybe a few hundred years. This is sometimes called the Quaternary extinction event, and for decades it's been attributed to a combination of climate change and overhunting by humans. But the Younger Dryas Impact hypothesis offers another explanation. An impact event would have instantly killed many large animals in the blast zones. The resulting climate change and ecosystem collapse would have finished off the rest. The fact that the timing of the extinction coincides so closely with the proposed impact is suggestive, to say the least. And here's where it gets really interesting from the perspective of this video. The Younger Dryas also coincides with the disappearance of the Clovis culture, which was the dominant archaeological culture in North America at the time. Clovis people were sophisticated hunter-gatherers who made distinctive stone tools and had spread across much of the continent. And then, right around 12,900 years ago, the Clovis culture essentially vanishes from the archaeological record. The population crashed, the distinctive tools stop appearing, and when people show up again in the record, they're making different tools and seem to have different cultural practices. For a long time, this was explained by the extinction of the megafauna. The Clovis people were specialized hunters who relied heavily on mammoths and other large game, and when those animals went extinct, their way of life collapsed. But the impact hypothesis suggests something more dramatic. If there were airbursts or impacts across North America, entire populations could have been wiped out instantly. The survivors would have faced a drastically altered landscape, with forests burned, water sources contaminated, and game animals either dead or driven away. Any complex societies that were developing, any early experiments with agriculture or permanent settlements would have been obliterated. And this is where we tie back into the Silurian hypothesis and the broader theme of this video. The Younger Dryas demonstrates that Earth's environment can be catastrophically altered on timescales that are shorter than a human lifetime. And when that happens, it doesn't just kill individuals or even species, it erases cultures, technologies, accumulated knowledge, all of it gone. If there had been early human civilizations developing complex societies before the Younger Dryas, and I'm not saying there were, but if there had been, we would have almost no way of knowing because the impact and the subsequent climate chaos would have destroyed the evidence. The Younger Dryas essentially reset human civilization. When it ended 11,700 years ago and the climate stabilized, humans had to start over. And within a few thousand years, we see the first true agricultural societies emerging in the Fertile Crescent, the first permanent settlements, the first monumental architecture. It looks like the beginning of civilization, and in a way it is. But it's a beginning that comes after an ending, a new chapter that follows a catastrophe so complete that we're still trying to piece together what actually happened. Both the PETM and the Younger Dryas teach us the same uncomfortable lesson. Earth's history is not a smooth, gradual progression. It's punctuated by sudden, violent upheavals that can erase everything that came before. And the evidence for these events, while it exists, is often so subtle or so localized that we're constantly in danger of missing it entirely. How many other planetary scars are there that we haven't found yet? How many times has the biosphere been reset? How many civilizations or ecosystems or entire evolutionary lineages have been wiped from existence so thoroughly that we'll never know they were here? And here's the really unsettling thought. If these kinds of catastrophic resets can happen on Earth on a timescale of thousands or millions of years, what about on cosmic timescales? What about events that reshape not just planets but galaxies or galaxy clusters or the universe itself? Because the more we learn about the cosmos, the more we're finding evidence that the universe has its own scars, its own violent history, its own moments of catastrophic change that reset the cosmic clock. And some of those scars are pointing to something that shouldn't exist, something that predates the current epoch of cosmic history. Something that was here before the Big Bang, or before whatever we think of as the beginning actually was. The planet remembers its traumas, even if we've forgotten them. And sometimes, when you look closely enough at the rocks, at the ice cores, at the sediment layers, you can see the scars. You can see the moments where everything changed, where the world as it was ended and the world as it is began. And each of those moments makes you wonder, what came before? What was lost? What was erased so completely that we're only now starting to realize we should be looking for it? Because if Earth can reset itself so thoroughly that entire epochs become invisible, what does that say about the possibility of even older resets, even more complete erasures, events so extreme that they don't just reshape a planet, but reshape reality itself? And that's a question that's going to lead us into some very strange territory. Because there's a place, an ancient site that was built right after the Younger Dryas ended, that challenges everything we think we know about early human civilization, a place that shouldn't exist according to our timeline, that required knowledge and organization that people supposedly didn't have yet, and that might, just might, be connected to whatever came before the catastrophe. We need to talk about Gobekli Tepe. Gobekli Tepe, the architects of the impossible. So we've just talked about how Earth can essentially hit the reset button on itself, how catastrophic events like the Paleocene-Eocene thermal maximum and the Younger Dryas can erase entire chapters of history so thoroughly that we're lucky to find any evidence they happened at all. We've explored how the geological record is incomplete, how 99% of the Earth's crust gets recycled over 100 million years, how civilizations could rise and fall and leave almost no trace. And we've established that 12,900 years ago, something absolutely catastrophic happened that wiped out most of North America's megafauna, triggered a sudden return to Ice Age conditions, and essentially reset human civilization. But here's where things get really interesting, and honestly pretty uncomfortable if you're someone who likes neat, tidy narratives about human history. Because right after the Younger Dryas ended, right when the climate stabilized and humans were supposedly still living in small, scattered bands of hunter-gatherers, barely scraping by, just figuring out how to make stone tools and hunt animals, something impossible happened. Someone, somewhere, decided to build the most sophisticated architectural complex that had ever existed on Earth up to that point. And they did it without any of the things we've been told are necessary for monumental architecture. No agriculture, no domesticated animals, no pottery, no metal tools, no writing, no cities, no permanent settlements. Nothing. Just hunter-gatherers who, according to every textbook ever written, should have been way too busy trying to survive to even think about organizing massive construction projects. This place exists. It's in southeastern Turkey, in a region that's now pretty arid and sparsely populated, but 11,000 years ago was probably a lot greener and more hospitable. It's called Gobekli Tepe, which translates to Potbelly Hill in Turkish, which is possibly the least dramatic name you could give to what is arguably the most important archaeological discovery of the past century. This site is so significant, so completely paradigm-shattering, that it's forced archaeologists to fundamentally rethink everything they thought they knew about the origins of civilization. And I mean everything. Let me give you the basic facts because they're absolutely staggering. Göbekli Tepe was built between roughly 9,500 and 8,000 years before the Common Era. That's 11,000 to 10,000 years ago, give or take a few centuries. To put that in perspective, Stonehenge was built around 2500 BCE, so it's about 7,000 years younger than Gobekli Tepe. The Great Pyramid of Giza was built around 2560 BCE, so it's about 6,500 years younger. The oldest cities we know of, places like Uruk and Eridu in Mesopotamia, date to around 4000 BCE at the earliest. Gobekli Tepe predates all of them by thousands of years. It's older than agriculture. It's older than writing. It's older than the wheel. It's older than everything we associate with civilization, and yet it exists, sitting on a hill in Turkey, impossible and undeniable. The site itself covers about 18 acres, and what's visible above ground is a tell, which is a mound formed by layers of human occupation over long periods of time. This particular tell is about 15 meters high, which is substantial. But here's the thing that absolutely blows my mind. We've only excavated about 5% of it. 5%. Geophysical surveys using ground-penetrating radar and magnetometry have revealed at least 20 large circular and oval structures buried beneath the surface, and we've only fully excavated a handful of them. Everything I'm about to describe is based on less than 5% of what's actually there. Just think about that for a second. What else is buried under that hill? So what did they find when they started digging? Massive stone enclosures, circular or oval in shape, surrounded by walls made of unworked stone. And in the center of each enclosure, pairs of enormous T-shaped limestone pillars, some of them over 5.5 meters tall and weighing more than 16 tons, 16,000 pounds. These aren't natural rock formations. These are carved megalithic pillars that were quarried from bedrock about a quarter-mile away, shaped into these distinctive T-shapes, transported to the site, and then erected in precise positions. And we're not talking about a couple of these pillars. We're talking about dozens, possibly hundreds of them across the entire site, arranged in these elaborate enclosures that show clear evidence of planning and organization. The T-shape is interesting because it's clearly meant to represent something. Most archaeologists who've studied the site believe the pillars are anthropomorphic, that they're stylized representations of human figures. The top of the T is the head, the vertical shaft is the body, and some of them have arms carved in relief on the sides, bent at the elbows with hands coming together over the belly. They're not realistic depictions, but they're clearly meant to evoke the human form. And they're all facing inward toward the center of each enclosure, like they're observing something or participating in some kind of gathering. But here's where it gets even weirder. These pillars are covered in carvings, intricate, detailed, sophisticated carvings of animals, foxes, lions, bulls, boars, snakes, vultures, scorpions, spiders, gazelles, onagers, which are a type of wild donkey. There are birds of prey, waterfowl, insects. The level of detail is extraordinary. You can see individual feathers on the birds, the musculature of the big cats, the scales on the snakes. This isn't primitive art. This is the work of skilled craftsmen who knew what they were doing and had the time and resources to do it well. And it's not just random animals either. The arrangement and selection of the animals seems deliberate, like they're telling a story or representing some kind of cosmological or mythological system. Some of the pillars also have abstract symbols carved on them. Crescent shapes, circles, H-shaped symbols, things that look like bags or buckets. And in 2023, a team led by Dr. Martin Sweatman from the University of Edinburgh published a study arguing that some of these carvings, specifically a series of V-shaped markings on one of the pillars in what's called Enclosure D, represent the world's oldest solar calendar. They claim it's a lunisolar calendar with 12 lunar months plus 11 extra days to keep it synchronized with the solar year, giving you 365 days total. And they argue that the carvings also incorporate knowledge of the precession of the equinoxes, which is the slow wobble of Earth's rotational axis that causes the position of the stars to shift over thousands of years. If they're right, and that's still being debated, it means someone at Gobekli Tepe understood astronomical cycles that we thought weren't discovered until Hipparchus figured them out in ancient Greece around 130 BCE. That's a gap of over 10,000 years. Dr. Sweatman's team also argues that other carvings at the site, particularly depictions of what looks like a comet or meteor shower, might be recording the Younger Dryas Impact event. They point to a specific pillar known as the vulture stone, which shows a headless man surrounded by vultures and various animals. They interpret this as a symbolic representation of the catastrophe, the headless man representing death, and the vultures representing the aftermath. Now, not everyone in the archaeological community agrees with this interpretation. Some think it's reading too much into the carvings, projecting modern knowledge onto ancient symbols that might have meant something completely different. But the fact that the timing lines up so perfectly that Gobekli Tepe was built right after the Younger Dryas ended is at the very least suggestive. So let's step back and think about what all of this means. We have a site that was built by hunter-gatherers, people who supposedly didn't have permanent settlements, didn't have agriculture, didn't have any of the social organization we associate with large-scale construction projects. And yet they managed to quarry, carve, transport and erect these massive stone pillars, build these elaborate enclosures and cover everything with sophisticated artwork. The logistics of this are mind-boggling. A single 16-ton pillar would require hundreds of people to move, even with ropes and sledges. The quarrying and carving would require specialized tools and skilled labor. The construction of the enclosures would need planning, coordination, leadership. Where did all of this come from? Klaus Schmidt, the German archaeologist who led the excavations at Gobekli Tepe from 1995 until his death in 2014, spent years trying to answer this question, and by his own admission, he never really figured it out. He called the site too enigmatic to comprehend, which is a pretty remarkable statement coming from the guy who spent 20 years studying it. Schmidt's working hypothesis was that Gobekli Tepe was a ritual center, a kind of pilgrimage site where hunter-gatherer groups from a wide region would periodically gather for ceremonies, feasts, and social bonding. He argued that the need to support these gatherings, to feed large numbers of people converging on the site, might have been one of the driving forces behind the development of agriculture. In other words, religion and ritual came first, and agriculture developed as a consequence, not the other way around. This completely inverts the traditional narrative, where we've always assumed that agriculture came first, creating food surpluses and permanent settlements, which then allowed people the leisure time to develop religion and build monuments. And there's evidence to support Schmidt's idea. Animal bones found at the site show that massive numbers of animals were slaughtered and consumed there. We're talking about thousands of gazelles, aurochs, which are wild cattle, and wild boar. The quantity of bones suggests large-scale feasting events, and the site doesn't appear to have been permanently inhabited. There are no domestic structures, no signs of everyday living. It was a place people came to, used for some specific purpose, and then left. But here's the problem with that explanation, and it's a big one. If Göbekli Tepe was a regional pilgrimage site, where are the settlements that these pilgrims were coming from? Where are the villages, the campsites, the infrastructure that would be necessary to support a population large enough to build this place? Because we've looked, and we haven't found them. There are a few contemporary sites in the region, small settlements with circular buildings, but nothing that would suggest the kind of population density or social organization you'd need to pull off something like Gobekli Tepe. It's like finding the Vatican in a world where nobody lives in houses yet. The Turkish government declared 2019 the year of Göbekli Tepe, and the Turkish culture minister Mehmet Nuri Ersoy called it the Pyramids of Southeast Turkey, which is honestly a pretty good comparison. Because just like the pyramids, Göbekli Tepe represents a level of social organization and technical capability that seems to appear out of nowhere. There's no clear developmental sequence. There are no earlier, simpler versions that we can point to and say, oh, they learned how to build small enclosures first, then gradually got better at it. Göbekli Tepe is sophisticated right from the start. The earliest layers are actually the most impressive. The pillars get smaller and less elaborate in the later phases of construction, not larger and more refined, which is the opposite of what you'd expect if this was a society gradually developing its architectural skills. And then, around 8,000 years ago, they buried it, deliberately. They filled in the enclosures with dirt and rubble, creating the tell that archaeologists found thousands of years later. Why would you do that? Why would you spend centuries or possibly millennia building this incredible complex and then just bury it? Some archaeologists think it was a ritual act, a way of closing or decommissioning the site. Others think it might have been done to preserve it, to protect it from something. We don't know. What we do know is that after it was buried, the site was essentially abandoned. Small groups occasionally visited the ruins over the next few thousand years, left some pottery and other artifacts, but the main construction and use phase was over. This abandonment coincides pretty closely with the development of agriculture in the region. The Neolithic Revolution, as it's called, when humans transitioned from hunting and gathering to farming and settled village life, was happening in this part of the world right around the time Göbekli Tepe was being abandoned. Places like Çatalhöyük, one of the earliest known cities, were being built. Jericho, one of the oldest continuously inhabited settlements, was growing. Wheat and barley were being domesticated. Sheep and goats were being herded. The world was changing, and Göbekli Tepe, this impossible monument built by hunter-gatherers, was being left behind. There's something almost tragic about that. This site represents an enormous investment of time, labor, and resources by people who lived in a fundamentally different way than we do. They didn't have the things we think of as necessary for civilization, and yet they built something that has lasted 11,000 years, and then they walked away from it, or their descendants did, and moved on to a new way of life. What knowledge was lost in that transition? What traditions, what stories, what understanding of the world did they have that we've forgotten? Because here's the thing that really gets me about Göbekli Tepe. The sophisticated astronomical knowledge that might be encoded in the carvings, the organizational capabilities required to build it, the artistic skill evident in the sculptures, none of this came out of nowhere. You don't just wake up one day and decide to build massive stone temples with complex astronomical alignments. You need accumulated knowledge, passed down over generations. You need a tradition of observation, of record-keeping, of teaching. You need a culture that values these things enough to invest the enormous effort required to create them. So where did that culture come from? Where are the precursors? Where are the stepping stones that led from simple hunter-gatherer bands to the architects of Gobekli Tepe? And this is where we circle back to the theme of this entire video. What if they didn't develop in isolation? What if the knowledge that went into building Gobekli Tepe was inherited from something that came before? Not necessarily an advanced civilization in the modern sense, but a previous chapter of human or even pre-human cultural development that was wiped out in the Younger Dryas catastrophe, leaving only fragments, only memories, only enough for the survivors to rebuild something extraordinary before the knowledge faded entirely. I know how that sounds. I know it sounds like I'm veering into ancient aliens or lost Atlantean civilizations or some other fringe nonsense. But I'm not talking about that. I'm talking about the simple observation that Gobekli Tepe exists, that it was built by people who supposedly didn't have the means to build it, and that it demonstrates knowledge and capabilities that appear fully formed without clear antecedents. The archaeological community is still grappling with this, still trying to reconcile the existence of the site with our models of how civilizations develop, and the uncomfortable truth is that our models might just be wrong. UNESCO designated Gobekli Tepe as a World Heritage Site in 2018, calling it one of the first manifestations of human-made monumental architecture. And they're right, but I think even that understates how profound this site is, because it's not just the first monumental architecture, it's proof that our entire narrative about the linear progression of human society from simple to complex, from primitive to advanced, is too simplistic. History doesn't move in a straight line. It moves in cycles, in spirals, with knowledge gained and lost and gained again. And sometimes, just sometimes, what looks like a beginning is actually a continuation, an echo of something that came before. The people who built Gobekli Tepe knew things. They understood celestial mechanics. They had mythological or cosmological systems complex enough to require these elaborate monuments. They could organize labor on a scale that rivals much later civilizations. And they did all of this with stone tools, without metal, without draft animals, without writing to record their plans and coordinate their efforts. It's impossible, except it's not, because it's sitting right there in Turkey for anyone to go and see. And here's the truly unsettling implication. If hunter-gatherers 11,000 years ago could do this, what else are we wrong about? What other assumptions about human capabilities, about the timeline of cultural development, about what was and wasn't possible in the deep past, are we making that are going to be overturned by the next discovery? because we've only excavated 5% of Göbekli Tepe. 5%. What's in the other 95%? What else is buried under tells and deserts and jungles around the world, waiting for someone to dig it up and force us to rewrite history again? The existence of Gobekli Tepe fundamentally challenges the narrative that civilization is a recent development, that complex societies only became possible with agriculture and cities. It suggests that humans, or at least some humans, have been capable of sophisticated thought and organization for much longer than we've given them credit for. And it raises the uncomfortable question of how many times this has happened before. How many times has human culture reached a level of complexity and knowledge that we would recognize as advanced, only to have it wiped out by catastrophe, leaving only scattered survivors to rebuild from fragments? This connects directly back to the Silurian Hypothesis and the question of pre-Big Bang existence. Because if we can't even reconstruct 11,000 years of human history without constantly being surprised by discoveries that shouldn't exist according to our models, how can we possibly hope to understand billions of years of cosmic history? How can we be certain that the Big Bang was the beginning when we're constantly finding evidence that things we thought were beginnings were actually middles or even endings? Gobekli Tepe is telling us something important, and I don't think we've fully listened yet. It's telling us that knowledge can persist through catastrophes, that it can be encoded in stone and symbol and story, passed down through generations even when the context is lost. It's telling us that what looks like the birth of civilization might actually be a rebirth, a reconstruction of something that existed before and was lost. And it's telling us that the universe, whether we're talking about human history or cosmic history, has a deeper memory than we've imagined, one that preserves echoes of what came before, even when the original events are erased. The architects of Gobekli Tepe built something impossible, and in doing so they left us a message across 11,000 years. They're telling us that the impossible is only impossible until it isn't, that our timelines and our models are provisional at best, and that there are always more chapters in the story than we've read. They're reminding us that beginnings are rarely as simple as they seem, that there's always context we're missing, always something that came before. And that brings us to the biggest question of all, the one that's been lurking beneath the surface of this entire video. If beginnings aren't really beginnings, if the Big Bang wasn't the start, if Earth's habitability goes back further than we thought, if civilizations can rise and fall and rise again, then what does that say about the nature of reality itself? Because all of these examples, from the cosmic microwave background anomalies to the ancient Zircons to Göbekli Tepe, they're all pointing in the same direction. They're suggesting that the universe isn't a one-time event with a clear beginning and a predetermined end. They're suggesting something much stranger, something that physicists have been theorizing about for decades but haven't been able to prove. They're suggesting that maybe, just maybe, the universe is cyclical, or perhaps not even singular at all, that what we call the Big Bang might just be one iteration in an endless series of cosmic cycles, or one bubble in an infinite multiverse where universes are constantly being born and dying. And if that's true, then the question isn't what came before the Big Bang. The question is what has always been there, waiting between the cycles, persisting through the deaths and births of universes. And that's a question that's going to take us deep into the cutting edge of theoretical physics and cosmology, into ideas that sound more like science fiction than science, but are being taken seriously by some of the brightest minds in the field. The multiverse, quantum foam, and cosmic cycles. So we've just talked about Gobekli Tepe, this impossible monument built by hunter-gatherers 11,000 years ago that demonstrates knowledge and organizational capabilities that shouldn't exist according to our timeline. We've explored how Earth can reset itself, how catastrophes can erase entire chapters of history, how the geological record is so incomplete that civilizations could have risen and fallen without leaving traces we'd recognize. And all of this has been building to one unavoidable conclusion. Our understanding of beginnings, whether we're talking about human civilization or the universe itself, is fundamentally incomplete. We keep finding evidence that what we thought were starting points were actually just transitions, continuations of something that came before. And that brings us to the biggest question of all, the one that physicists have been wrestling with for decades, the one that ties all of these threads together. If the Big Bang wasn't the beginning, if there was something before it, what was it? And more importantly, how do we even begin to think about a question like that when our entire framework of physics breaks down at the moment of the Big Bang itself? Because that's the real problem here. We can trace the universe back to a fraction of a second after the Big Bang, back to the Planck time, that impossibly tiny 10 to the negative 43 seconds we talked about earlier. But before that, we've got nothing. Our equations produce infinities, our models collapse, and we're left staring at a wall we can't see past. But here's the thing that absolutely blows my mind. Some of the smartest people in physics have been working on this problem, and they've come up with answers. Not definitive, proven answers, because we're talking about events and conditions that are literally impossible to test directly. But they've developed theoretical frameworks that are mathematically consistent, that don't violate known physics, and that offer genuine solutions to the question of what came before. And these frameworks are so strange, so far removed from everyday experience, that they sound like science fiction. Except they're not. They're serious scientific proposals being published in peer-reviewed journals by Nobel Prize winners and leading cosmologists. The first, and probably most famous of these frameworks, is the multiverse. Now, I know what you're thinking. The multiverse is a comic book thing, right? It's Marvel movies and parallel dimensions where there's an evil version of you with a goatee. And yeah, pop culture has absolutely run wild with the concept. But the scientific multiverse, the one that physicists actually talk about, is based on solid theoretical ground and emerges naturally from some of our best models of how the universe works. There are actually several different types of multiverse theories, and they come from completely different areas of physics, which is kind of remarkable. It's like multiple roads all leading to the same destination, which suggests that maybe there's something real there. The most well-known version comes from something called eternal inflation, which is an extension of the inflation theory we touched on earlier. Remember how we talked about cosmic inflation, that period of exponential expansion that happened before the hot Big Bang? Well, it turns out that in most models of inflation, once it starts, it never completely stops. Here's how it works. Inflation is driven by something called the inflaton field, which is basically a quantum field that permeates space and has a certain energy density. When this field is in a high energy state, space expands exponentially. When it drops to a lower energy state, inflation stops, and that energy gets converted into matter and radiation, creating what we call the hot Big Bang. That's what happened in our observable universe about 13.8 billion years ago. But here's the kicker. The inflaton field is subject to quantum fluctuations, those random ups and downs we talked about earlier. So even as some regions of space are dropping out of inflation and creating universes, other regions are getting quantum kicks that push them back into a high-energy state, causing them to keep inflating. The result is what Alan Guth, one of the founders of inflation theory, calls eternal inflation. Once inflation starts anywhere, it creates an infinite amount of space, and within that space, there are constantly regions dropping out of inflation and forming pocket universes, bubble universes, each with their own Big Bang. Our universe is just one of these bubbles, and the space between the bubbles is still inflating, creating more space, more bubbles, more universes, forever. It never ends. There was no beginning to the process as a whole because the inflating space is eternal into the past and future. Now let me be clear about what this means. We're not talking about parallel dimensions or alternate timelines. We're talking about actual physical regions of space that are so far away from us that we could never reach them, even traveling at the speed of light for the entire age of our universe. The space between us and these other universes is expanding faster than light can cross it, so they're permanently causally disconnected from us. We can never see them, visit them, or communicate with them. For all practical purposes, they're as unreachable as something that doesn't exist. But mathematically, according to our best models of inflation, they're out there. And here's where it gets really wild. In eternal inflation, every possible configuration of matter and energy, every possible set of physical laws, every possible history exists somewhere in the multiverse. There are universes where the constants of nature are slightly different, where electrons are a bit heavier or the speed of light is a bit slower. There are universes where stars never form because the nuclear forces aren't strong enough. There are universes that collapse back in on themselves milliseconds after forming, and there are universes that are almost identical to ours, differing only in tiny quantum events that cascade into macroscopic differences. The number of universes is not just large, it's infinite, and in an infinite multiverse, everything that can happen does happen, somewhere, infinitely many times. André Linde, one of the architects of eternal inflation theory, has said that trying to find the beginning of the multiverse is like trying to find the edge of the Earth. It's a question that doesn't make sense because there is no edge, no beginning. The multiverse just is, eternally inflating, eternally creating new universes. Our Big Bang wasn't the beginning of everything. It was just the beginning of our little corner of an infinite cosmic landscape. But eternal inflation isn't the only game in town when it comes to multiverses. There's another version that comes from string theory, which is this incredibly complex mathematical framework that tries to unify quantum mechanics and general relativity. Now, I'm not going to pretend to fully understand string theory. Nobody fully understands string theory. The math is so abstract and so far removed from anything we can test that even the physicists working on it will admit they're not sure if it's actually describing reality or just an incredibly elegant mathematical structure that happens to look like physics. But one of the predictions that comes out of string theory is that there are a huge number of possible vacuum states, possible configurations of the fundamental fields that make up reality. The number that gets thrown around is 10 to the power of 500, which is a 1 followed by 500 zeros. That's more configurations than there are atoms in the observable universe, by a factor that's too large to even comprehend. And each of these configurations corresponds to a different set of physical laws, different particle masses, different force strengths. String theorists call this the string landscape, and the idea is that different regions of the multiverse might settle into different points on this landscape, creating universes with radically different physics. This version of the multiverse doesn't require eternal inflation, although the two ideas work well together. The string landscape suggests that our universe, with its particular values for the constants of nature, is just one possibility among an incomprehensibly vast number of others. And if you combine this with eternal inflation, you get a picture where the multiverse is not only infinite in extent, but also infinite in variety. Every possible universe that could exist does exist somewhere. Now, I can already hear the objections, and they're valid. The multiverse is not directly testable. We can't observe other universes. We can't visit them. We can't even send signals to them. So how is this science? How is this different from just making stuff up? And that's a fair criticism. Some physicists, including very prominent ones, have argued that the multiverse is metaphysics masquerading as physics, that it's untestable and therefore unscientific. But here's the thing. The multiverse isn't something physicists invented because they wanted to believe in it. It's something that falls out of theories that were developed for completely different reasons. Inflation was developed to solve very specific problems with the standard Big Bang model. Problems like the horizon problem and the flatness problem. String theory was developed to reconcile quantum mechanics and gravity. Nobody set out to create a multiverse theory. The multiverse emerged as a consequence of trying to solve other problems, and that gives it a certain credibility, at least to some physicists. It's not an ad hoc addition, it's a prediction, and there are indirect ways to test it. If our universe is part of a multiverse created by eternal inflation, we might see evidence in the cosmic microwave background. If another bubble universe collided with ours in the distant past, it would leave a distinctive signature, a kind of bruise in the CMB. Several groups have looked for this, and so far they haven't found anything definitive, but the search continues. The absence of evidence isn't evidence of absence, especially when you're looking for something that might be incredibly rare or subtle. But let's step back from the multiverse for a second and talk about another framework that addresses the question of what came before the Big Bang, and this one doesn't require infinite universes or eternal inflation. It's called quantum cosmology, and it deals with the idea that the universe itself emerged from quantum mechanics, that the Big Bang was essentially a quantum event. In quantum mechanics, particles can spontaneously appear out of the vacuum. We've talked about this before with virtual particles and quantum fluctuations. The vacuum isn't empty, it's full of energy, and that energy can temporarily manifest as particle-antiparticle pairs that pop into existence and then annihilate each other. This is happening all the time, everywhere, and we've measured it. The Casimir effect, which was conclusively measured in 2001, is direct evidence that quantum fluctuations are real. When you place two metal plates very close together in a vacuum, the quantum fluctuations between the plates are restricted compared to the fluctuations outside, creating a measurable force that pushes the plates together. This isn't theory, this is observed fact. But if particles can pop into existence from nothing, what about universes? This is the question that quantum cosmology asks, and the answer is genuinely bizarre. At scales approaching the Planck length, which is about 1.6 times 10 to the negative 35 meters, space-time itself becomes subject to quantum fluctuations. John Wheeler, the physicist who coined the term black hole and was one of the giants of 20th century physics, described this in 1955 as quantum foam. He said that at the Planck scale, space and time would be continuously changing, transforming, writhing, with tiny black holes and wormholes constantly forming and disappearing. The smooth, continuous space-time we experience at large scales would, at the smallest scales, be more like foam, bubbling and roiling with quantum uncertainty. Wheeler described it beautifully. He said, "The continuous space and time of classical physics would be transformed into a randomly fluctuating state. It's not that space-time is sitting there calmly at the Planck scale. It's violent, chaotic, constantly creating and destroying tiny structures that exist for impossibly brief moments before vanishing. This isn't empty nothingness. This is quantum foam, and it's the most fundamental substrate of reality we know of. And here's where it connects to the origin of the universe. If space-time is subject to quantum fluctuations at the Planck scale, then the Big Bang could be understood as a particularly large quantum fluctuation, a statistical anomaly where a region of quantum foam happened to fluctuate into something we'd recognize as a universe. The entire cosmos, with all its matter and energy, could have emerged from nothing in the same way that virtual particles emerge from the vacuum. Except instead of lasting for a tiny fraction of a second before disappearing, this particular fluctuation kept growing, kept inflating, eventually becoming the universe we live in. This idea is supported by some genuinely mind-blowing mathematics. When you apply quantum mechanics to the universe as a whole, using something called the Wheeler-DeWitt equation, you get solutions that describe universes spontaneously appearing from nothing. And by nothing, I mean literally nothing. No space, no time, no matter, no energy. Just the quantum mechanical potential for something to exist, encoded in the mathematics of quantum field theory. The physicist Alexander Vilenkin at Tufts University has argued that the universe could have tunneled into existence from literally nothing through a quantum process. He calls it the universe from nothing proposal, and it's based on solid quantum mechanics, not speculation. But here's the part that really bends my brain. In this framework, the question of what came before the Big Bang doesn't make sense because time itself began with the Big Bang. There was no before because before is a temporal concept and time didn't exist yet. It's like asking what's north of the North Pole. The question is grammatically correct but physically meaningless. Vilenkin has said the universe is most likely to have started in a state that has the smallest possible energy. And what state is that? It's nothing. But that nothing isn't empty void. It's quantum foam, seething with potential, capable of spontaneously producing universes. And this brings us to a genuinely surprising fact that doesn't get talked about enough. The quantum foam, this violent, fluctuating substrate at the Planck scale, might actually solve one of the biggest problems in physics. It's called the cosmological constant problem, and it's been driving physicists crazy for decades. Here's the issue. When you calculate the energy density of empty space, the vacuum energy, using quantum field theory, you get a number that's about 10 to the power of 120 times larger than what we actually observe. That's not a typo. The theoretical prediction is off by 120 orders of magnitude. It's arguably the worst prediction in the history of physics. But Stephen Carlip at UC Davis has developed a model that uses quantum foam to solve this. The idea is that at the Planck scale, space is made up of these tiny regions that are constantly expanding and contracting, appearing and disappearing. When you average over all of these fluctuating regions, when you glue them together to get the macroscopic spacetime we experience, the huge vacuum energy contributions from each individual region cancel out, giving you a net value that's basically zero. The quantum foam, the thing that makes spacetime so chaotic at the smallest scales, is also the thing that stabilizes it at large scales. It's elegant, it's mathematically consistent, and it might actually be how the universe works. There's also a recent paper from 2023 that shows you don't even need the inflaton field to explain inflation. You can get the same exponential expansion just from quantum foam and its gravitational effects in a universe with a cosmological constant. The gravitational waves produced by the churning quantum foam naturally create the kind of pattern we see in the cosmic microwave background, without needing to invent new fields or particles. It's remarkable how this idea of quantum foam, which was just a theoretical speculation by John Wheeler in the 1950s, keeps showing up as a crucial ingredient in our best models of how the universe works. And this is why physicists take quantum foam seriously. It's not just an abstract mathematical curiosity. It has real, measurable consequences. The electron magnetic moment, which is one of the most precisely measured quantities in physics, matches the theoretical prediction to 12 decimal places when you include the effects of quantum foam in the calculation. Without the foam, the prediction is off by about 0.1%, which doesn't sound like much, but in physics that's a catastrophic failure. With the foam, it's perfect. That's how we know quantum foam is real, or at least that something very much like it is happening at the Planck scale. Lee Cronin, a chemist who does a lot of work on the origin of life and quantum evolution, put it really well. He said, "Quantum physics reveals the universe as a field of probabilities, full of entirely random sequences. That's what quantum foam is. It's not deterministic, it's not predictable. It's a roiling sea of probabilities where anything that can happen will happen, given enough time. And out of that chaos, ordered structures emerge. Particles, atoms, molecules, stars, galaxies, life, consciousness, all of it emerging from the quantum foam like islands of order in an ocean of randomness." And this connects directly to what we've been talking about throughout this video. The idea that there was nothing before the Big Bang is fundamentally wrong. There was quantum foam. There was the mathematical structure of quantum field theory. There was potential. There was something. And that something is eternal. It didn't begin. It doesn't end. It just is. The Big Bang was a local event, a fluctuation in an eternal quantum substrate that has always existed and always will exist. Now, there's one more framework we need to talk about, and it's my personal favorite because it's the most audacious. It's called the cyclic universe model, and it suggests that the Big Bang wasn't a one-time event, but one in an infinite series of cosmic cycles. The universe expands, eventually stops expanding, contracts back down, and then bounces, creating a new Big Bang. Over and over, forever, with no beginning and no end. There are a few different versions of this idea. The simplest is the oscillating universe, which was popular in the mid-20th century, but fell out of favor when we discovered that the universe's expansion is accelerating, not slowing down. If the expansion is accelerating, there's no way for it to reverse and collapse back into a big crunch. The universe will just keep expanding forever, getting colder and emptier until it reaches heat death. That's the standard model prediction. But more recent versions of cyclic cosmology get around this problem using ideas from string theory. In a model called brane cosmology, our universe is a three-dimensional brane, like a membrane, floating in a higher dimensional space. There are other branes out there, and occasionally they collide. When two branes smash into each other, the energy of the collision creates matter and radiation, essentially producing a Big Bang. The universe expands. Eventually the expansion slows and reverses due to the dynamics of the higher dimensional space, and the branes collide again, creating another Big Bang. This can go on forever, cycling eternally. In this model, the Big Bang is just the moment of collision between branes. Before our Big Bang, there was a previous cycle, and before that, another, stretching back infinitely into the past. There's no beginning because the cycles are eternal. Time doesn't start, it just keeps going, cycle after cycle, with each universe living and dying and being reborn. Paul Steinhardt at Princeton and Neil Turok at the Perimeter Institute have been the main proponents of cyclic models, and they've developed the math in impressive detail. The model makes predictions that are subtly different from standard inflation, particularly in the pattern of gravitational waves left over from the Big Bang. So far, the observations are consistent with both models, but future experiments, particularly those looking at the polarization of the cosmic microwave background, might be able to distinguish between them. The beautiful thing about cyclic models is that they solve a lot of philosophical problems. They don't require a beginning, so you don't have to explain where the universe came from. They don't require fine-tuning, because the universe has had infinite time to settle into its current state. And they suggest that the second law of thermodynamics, the one that says entropy always increases, might not be absolute. Each cycle resets the entropy, wiping the slate clean for the next universe. But the real reason I love cyclic models is that they fit so perfectly with everything else we've been talking about. Earth resets itself through catastrophes, Civilizations rise and fall and rise again. Knowledge is lost and rediscovered. And maybe the universe works the same way. Maybe the cosmos has a memory that persists through the cycles, encoded not in rocks or ruins, but in the quantum fields that survive from one cycle to the next. Maybe the anomalies we see in the cosmic microwave background aren't just random fluctuations, but echoes from previous cycles, information bleeding through from universes that existed before ours. Roger Penrose, the Nobel Prize-winning physicist, has proposed something along these lines called conformal cyclic cosmology. His idea is that the universe goes through infinite cycles, and information from previous cycles can leak into the next one, showing up as subtle patterns in the CMB. He's even claimed to have found evidence of this, circular patterns in the CMB that might be the signatures of black hole collisions from a previous cosmic epoch. The physics community is divided on whether he's right, but the fact that someone of Penrose's caliber is seriously proposing this tells you how far we've come from thinking of the Big Bang as the absolute beginning. All of these frameworks, the multiverse, quantum cosmology, cyclic models, they're all saying the same thing from different angles. The Big Bang was not the beginning of everything. It was a local event, a transition, a moment in a much larger story that has no beginning and no end. The universe, or the multiverse, or the quantum foam, or whatever you want to call the fundamental substrate of reality, is eternal. It has always existed in some form, and it always will. And this is the conclusion that all of our evidence has been pointing toward. The anomalies in the cosmic microwave background that don't quite fit the standard model, the ancient zircons that preserve signatures from before Earth existed, the Silurian Hypothesis showing us that even recent history can be almost completely erased, the planetary scars demonstrating how thoroughly events can reset the geological record, Göbekli Tepe proving that beginnings aren't as simple as they appear. All of it points to the same uncomfortable truth. What we call beginnings are just transitions, moments where one chapter ends and another begins, but the story itself has no first page. The implications of this are genuinely staggering. If the universe is eternal, if the Big Bang was just one event in an infinite series or one bubble in an infinite multiverse, then everything we thought was unique about our existence, everything we thought was special about this moment in cosmic history, is just one instance among infinitely many. There have been universes before ours, and there will be universes after ours. There might be civilizations out there that are billions of years older than us, that have been through multiple cosmic cycles, that have learned things about the nature of reality that we can't even imagine. And maybe, just maybe, they left traces, not physical artifacts that would survive a big crunch or a transition between universes, but information encoded in the quantum foam itself, in the patterns of the cosmic microwave background, in the values of the fundamental constants. Maybe the universe we live in isn't a blank slate. Maybe it's been written on before, edited, revised over and over through infinite cycles. And maybe if we look closely enough, if we develop the right tools and ask the right questions, we can read what was written before. Because here's the thing that really keeps me up at night. If all of this is true, if the universe is eternal and cyclic, or if we're one bubble in an infinite multiverse, then the question isn't what came before the Big Bang. The question is what has been there all along, waiting between the cycles, existing in the space between universes, watching as reality after reality is born and dies and is born again. What persists when everything else changes? What endures when universes collapse and new ones emerge? What was there before the beginning, and what will be there after the end? And that's not a question physics can answer with equations and observations. That's a question about the nature of existence itself, about whether there's something fundamental and eternal that underlies all of reality, something that was never created and can never be destroyed, something that just is. And if there is, what is it? Is it just the quantum foam, the mathematical structure of physics itself? Or is it something more, something that has awareness, intention, purpose? Because if the universe can spontaneously emerge from quantum fluctuations, if matter and energy and space and time can arise from nothing, then consciousness, the thing that's reading these words right now, trying to understand its place in the cosmos, where did that come from? Did it emerge from the quantum foam too? Or was it there before, waiting for a universe to exist so it could experience itself? These are the questions that physics is bringing us to, whether it intended to or not. And they're the same questions that ancient cultures asked when they looked up at the stars and wondered where it all came from. We've just replaced gods and creation myths with quantum fields and multiverses, but the fundamental mystery remains. Why is there something rather than nothing? And if there's always been something, what has it been doing all this time? The silence of the cosmos is deafening. We've been searching for signs of other civilizations, other intelligences for decades, and we've found nothing. No radio signals, no megastructures, no evidence that anyone else is out there. But maybe we've been looking in the wrong places or listening for the wrong signals. Because if there's something that predates the Big Bang, something eternal and fundamental, it wouldn't necessarily communicate through radio waves or build Dyson spheres. It would be woven into the fabric of reality itself, present in every quantum fluctuation, every particle interaction, every moment of existence. It would be the universe experiencing itself, through us, through every conscious being that has ever existed or ever will exist. And maybe the reason we haven't heard from it is because we are it, and we just haven't realized it yet. The silence. What was already waiting? So we've just spent the last hour diving into some genuinely mind-bending territory. We've talked about how the Big Bang might not actually be the beginning, how quantum foam is the seething, chaotic substrate underlying all of reality, how the universe might be one bubble in an infinite multiverse or one cycle in an eternal series of cosmic deaths and rebirths. We've explored ancient zircons that remember events from before Earth existed, contemplated the possibility of pre-human civilizations that vanished so completely we can barely detect their traces, examined planetary catastrophes that reset the geological record, and stood in awe of Gobekli Tepe, that impossible monument built by people who supposedly didn't have the means to build it. And all of this, every single piece of evidence we've discussed, has been pointing toward one unavoidable, deeply uncomfortable conclusion. What we call the beginning wasn't the beginning at all. It was just a moment of transition in a story that has no first chapter. But here's where we need to stop and really think about what that means. Because it's one thing to say the universe is eternal, that the Big Bang was just one event among infinitely many. It's another thing entirely to sit with the implications of that statement and realize how fundamentally it changes everything. Every assumption we've made about our place in the cosmos, every sense we've had that we're special or unique, or that this moment in history matters, all of it gets challenged when you accept that the universe has been doing this forever, that there have been infinitely many Big Bangs before ours, infinitely many universes before this one, infinitely many civilizations that rose and fell and were forgotten completely. That the story we're part of isn't a novel with a beginning, middle, and end. It's one page in an infinite book that's been written and rewritten so many times that nobody remembers what the first draft said. Let me take you back through everything we've covered because I think it's important to see how all of these pieces fit together. We started with the Big Bang's shadow, looking at the cosmic microwave background and realizing that the standard story of the universe emerging from nothing 13.8 billion years ago has some serious holes in it. The anomalies in the CMB, the patterns that don't quite fit the models, the evidence for cosmic inflation that pushes the actual origin back even further, all of it suggesting that the hot Big Bang we learned about in school wasn't the beginning but just the point where something that was already happening became visible to us. Then we looked at those ancient zircon crystals from Jack Hills in Western Australia, 4.4 billion years old, preserving chemical signatures that tell us Earth had liquid water and potentially habitable conditions just a few 100 million years after the planet formed. This completely overturned our understanding of the Hadean eon, that supposed hellscape of molten rock and constant bombardment. Turns out Earth was ready for life far earlier than we ever imagined. And those zircons, those virtually indestructible time capsules, they're carrying isotopic signatures from materials that predate our solar system, atoms that were forged in stars that died billions of years before our sun was born. They're telling us that information can be preserved across timescales that approach the age of the universe itself, that the cosmos has a memory written in stone and crystal and the very atoms that make up our world. Then we confronted the Silurian Hypothesis, that deeply unsettling thought experiment asking whether we could even detect the traces of an industrial civilization if it had existed on Earth millions of years ago. And the answer, the one that keeps me up at night, is probably not. The geological record is so incomplete, so heavily recycled by plate tectonics, that 99% of the Earth's crust gets melted and reformed over 100 million years. An entire civilization could have risen, flourished, and vanished, leaving only subtle chemical signatures and isotopic anomalies that we'd never find unless we knew exactly what to look for. And if that's true for Earth over the span of 100 million years, what does it say about the universe over the span of billions or even infinite time? We examined the planetary scars, the Paleocene-Eocene thermal maximum and the Younger Dryas, demonstrating that Earth can and does hit the reset button on itself. Catastrophic climate shifts that happen in decades, not millennia. Impact events that wipe out entire ecosystems and possibly nascent human civilizations. The geological evidence showing us that what looks like stability is actually just the calm period between catastrophes, and that given enough time, everything gets erased. The rocks, remember, if you know how to read them, but they're constantly being overwritten, constantly being recycled, constantly losing the details of what came before. And then Göbekli Tepe, that monument in Turkey that shouldn't exist, built by hunter-gatherers 11,000 years ago with knowledge and organizational capabilities that appear fully formed without clear precursors. Massive T-shaped pillars weighing 16 tons, carved with sophisticated astronomical observations, possibly recording the Younger Dryas Impact event in stone. A place that demonstrates human civilization isn't a linear progression from simple to complex, but something that rises and falls and rises again, that knowledge can be inherited from previous iterations, that beginnings are almost never as simple as they appear. The fact that we've only excavated 5% of that site, and already it's forced us to completely rethink the timeline of human cultural development, should tell you everything you need to know about how much we still don't understand. And finally, we dove into the cutting edge of theoretical physics and cosmology. The multiverse emerging from eternal inflation, infinite bubble universes being born from an inflating space that never stops expanding. Quantum cosmology showing us that the vacuum isn't empty, but full of roiling quantum fluctuations, quantum foam that John Wheeler described as the violent, chaotic substrate of spacetime at the Planck scale. And cyclic universe models suggesting that the Big Bang was just one beat in an eternal rhythm of expansion and contraction, birth and death and rebirth, with information possibly leaking through from previous cosmic epochs into our own. Every single one of these pieces of evidence, from the largest cosmological scales to the smallest quantum fluctuations to the archaeological sites on our own planet, they're all telling the same story. The universe, or the multiverse, or whatever you want to call the totality of existence, is eternal. It has always been here in some form. And that means the Big Bang, that supposed moment of creation, wasn't creation at all. It was just a phase transition, a moment where one state of reality shifted into another. The universe didn't begin 13.8 billion years ago. Something that was already there transformed into what we now call the universe. And this is where we have to confront the really disturbing implications of all of this. Because if the universe didn't have a beginning, if existence is eternal, then every assumption we've made about our uniqueness, about our significance, about this moment in cosmic history being special, all of it falls apart. We're not the first. We're not unique. We're not even particularly early in the cosmic story. We're just one iteration among infinitely many, one brief moment of consciousness arising from the quantum foam, looking around, asking questions, and eventually fading back into the chaos from which we came. The philosopher Nick Bostrom at Oxford has written extensively about what he calls the simulation hypothesis, the idea that we might be living in a computer simulation created by a vastly more advanced civilization. And while I'm not necessarily endorsing that specific idea, the underlying logic is sound. If civilizations can reach a point where they're capable of creating detailed simulations of universes, and if those simulations can themselves contain conscious beings, then the number of simulated universes vastly outnumbers the number of real ones, which means statistically we're far more likely to be living in a simulation than in base reality. It's a disturbing thought, but it follows logically from the assumption that consciousness can persist long enough to develop that kind of technology. But here's what really gets me about Bostrom's argument and how it connects to everything we've been talking about. If the universe is eternal, if there have been infinite cosmic cycles or infinite bubble universes, then the probability that we're in the first universe, the base reality, the one that wasn't created by something else, is literally zero, because any finite number divided by infinity is zero. If there have been infinitely many universes before ours, and if even a tiny fraction of them developed civilizations capable of creating simulated realities, then the number of simulated universes is infinite, and the number of base realities is one. We lose the lottery by definition. Now, I'm not saying we're definitely living in a simulation. I'm saying that once you accept that existence is eternal, once you accept that the Big Bang wasn't the beginning, you have to grapple with the implications of that. And one of those implications is that we might not be as fundamental or as real as we think we are. We might be an echo, a reflection, a simulation, a dream, something that exists because something else that came before decided to create us or observe us or imagine us into being. And this connects to something that physicists have been noticing for a while but don't like to talk about because it sounds too philosophical, too metaphysical. The universe appears to be fine-tuned for our existence. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, they're all set to very specific values. And if those values were even slightly different, atoms couldn't form, stars couldn't shine, planets couldn't exist, life couldn't arise. The range of values that allows for a universe anything like ours is incredibly narrow. Change the gravitational constant by 1 part in 10 to the 60th, and stars don't form. Change the strong nuclear force by a few percent, and protons fall apart. The universe is balanced on a knife's edge. The standard explanation for this is the anthropic principle. We observe these particular values because if they were different, we wouldn't be here to observe them. In a multiverse with infinite variations, every possible set of constants exists somewhere, and we necessarily find ourselves in one of the universes where the constants allow for observers like us. It's selection bias, essentially. We're not special, we just happen to be in one of the universes that works. But there's another interpretation that's harder to dismiss once you start thinking about it. What if the constants are set the way they are because something set them? What if the universe isn't randomly fine-tuned but deliberately configured? What if the eternal substrate underlying reality, whether it's quantum foam or the multiverse, or some higher dimensional structure we can't even conceive of? What if it has intention? What if it's conscious? I know how that sounds. I know it sounds like I've gone full New Age mysticism or ancient astronaut theory or something, but I'm not talking about gods or intelligent design in any religious sense. I'm talking about the possibility that consciousness isn't something that emerged from the universe, but something that's fundamental to it. That awareness, observation, the subjective experience of existence might be as basic to reality as space and time and energy. That the quantum foam isn't just randomly fluctuating, but is in some sense observing itself, experiencing itself, creating itself. There's a concept in quantum mechanics called the observer effect. It's been experimentally verified thousands of times and is one of the most solidly established facts in all of physics. When you measure a quantum system, when you observe it, the act of observation changes the system. Before you measure it, particles exist in a superposition of all possible states. The moment you observe it, the wave function collapses and the particle takes on a definite state. The observer isn't separate from the observed. The act of observation creates reality. John Wheeler, that same physicist who described quantum foam, spent the last decades of his life working on something he called the participatory anthropic principle. His idea was that observers aren't just passive witnesses to the universe, but active participants in bringing it into existence. He said, "We are participators in bringing into being not only the near and here, but the far away and long ago." Wheeler believed that the universe requires observers to exist, that without consciousness to collapse the wave function, reality would remain in an indeterminate state of pure possibility. The past, in Wheeler's view, isn't fixed until we observe it. We create history by measuring it. Now, most physicists think Wheeler went too far with this, that he was reading too much philosophy into quantum mechanics. But the mathematical structure of quantum mechanics really does suggest that observation plays a fundamental role in determining reality. And if that's true, if consciousness is somehow necessary for the universe to exist, then what was observing before conscious beings like us evolved? What was collapsing the wave function in the first moments after the Big Bang, or during the previous cosmic cycles, or in the space between universes? The uncomfortable answer that some physicists are starting to consider is that maybe something was. Maybe the quantum foam itself has a kind of proto-consciousness, a basic form of awareness that comes from the act of self-observation. Maybe the universe is observing itself into existence at every moment, and conscious beings like us are just local concentrations of that universal awareness, brief moments where the cosmos becomes aware of itself. Andre Linde, one of the architects of eternal inflation, has said that consciousness might be just as fundamental as space and time. He's argued that the way we think about consciousness as an emergent property that arises from complex arrangements of matter might be backwards. Maybe matter is what emerges from consciousness, from the act of observation. Maybe the quantum foam is full of primitive awareness, and evolution is just the process of that awareness becoming more organized, more complex, more capable of observing and understanding itself. I'm not saying this is definitely true. I'm saying it's a possibility that we can't rule out, and it's a possibility that becomes more plausible once you accept that existence is eternal. Because if the universe has been going through infinite cycles, if there have been infinitely many Big Bangs, infinitely many opportunities for consciousness to arise, then consciousness has had infinite time to evolve, to become more sophisticated, to learn how to persist through cosmic catastrophes and phase transitions. What would consciousness look like after billions or trillions of years of evolution? After surviving the deaths and births of entire universes, would we even recognize it as consciousness? Or would it be so alien, so far beyond our understanding, that it would look like a fundamental force of nature? And this brings us to the most unsettling question of all, the one that the title of this chapter is hinting at. If something was there before the Big Bang, if the quantum foam is eternal and possibly conscious, then what was it doing? Was it waiting? Was it watching? Was it preparing? Because here's the thing that really gets me. The universe appears to be designed for observers. The constants are fine-tuned to allow for complex chemistry and stable atoms and stars that live long enough to create heavy elements and planets that can harbor life. The cosmic microwave background has those tiny fluctuations that seeded the formation of galaxies in exactly the pattern needed for structure to form. The quantum foam produces virtual particles in exactly the way needed to stabilize the vacuum energy. Everything seems to work together, almost too well, almost like it was planned. And if it was planned, if the structure of reality was set up to allow for consciousness to emerge, then by whom or by what? The religious answer is God, some external creator that exists outside the universe and made it for purposes we can't understand. But if the universe is eternal, if there was no beginning, then there's no moment of creation, no point where an external creator could have intervened. Whatever is responsible for the structure of reality has to be part of reality itself, inherent in the quantum foam, woven into the fabric of existence at the deepest level. This is what I mean when I say the silence is deafening. We've been listening for signals from other civilizations for decades. SETI, the search for extraterrestrial intelligence, has been scanning the skies with radio telescopes since the 1960s. We've analyzed millions of star systems. We've examined thousands of exoplanets. We've looked for signs of megastructures, Dyson spheres, artificial radio emissions, laser pulses, anything that would indicate someone else is out there. And we've found nothing. Absolute silence, not a whisper. The Fermi paradox asks why this is. If the universe is so old and so big, if there are billions of potentially habitable planets in our galaxy alone, where is everybody? Why haven't we heard from anyone? The usual explanations involve the idea that civilizations don't last very long, that they destroy themselves before they can spread to other stars, or that space is just too big and travel is too slow, and the odds of two civilizations existing at the same time, in a way where they could detect each other, are vanishingly small. But there's another explanation that nobody likes to talk about because it's too weird, too unsettling. What if the silence isn't because nobody's out there? What if it's because everyone who gets advanced enough stops broadcasting? What if the reason we don't hear anyone is because once you reach a certain level of understanding, once you figure out how the universe really works, once you discover the eternal nature of existence and the role of consciousness in creating reality, you realize that broadcasting your presence is a mistake, that drawing attention to yourself is dangerous? Because if consciousness is fundamental, if the universe is in some sense aware, then maybe it notices when local concentrations of awareness become too sophisticated, too organized, too capable of understanding what's really going on. Maybe the silence is protective. Maybe every civilization that survives long enough learns to be quiet, to avoid attracting the attention of whatever it is that's woven into the fabric of reality, watching, waiting, observing. I know how paranoid that sounds. I know it sounds like I've gone completely off the deep end. But think about everything we've discussed. The universe is fine-tuned for consciousness to arise. The act of observation creates reality. The quantum foam is eternal and possibly aware. Information persists through cosmic cycles. What came before the Big Bang might still be here, encoded in the structure of space-time itself, in the patterns of the cosmic microwave background, in the fluctuations of the quantum vacuum. And if it's still here, if there's some form of awareness or structure or intent that predates the current universe and will survive its end, then we're not alone. We've never been alone. We're part of something vastly older and larger than ourselves, something that was here before the Big Bang and will be here after the heat death of the universe, something eternal. The philosopher Thomas Nagel wrote an essay in the 70s called "What is it like to be a bat?", arguing that we can never truly understand subjective experience from the inside of another consciousness. We can describe the physical processes of a bat's echolocation. We can map the neural pathways. We can explain the physics, but we can never know what it feels like to be the bat, to experience the world through echolocation. The subjective experience is forever inaccessible to us. Now apply that logic to the universe itself. If the quantum foam is conscious in some sense, if there's awareness inherent in the structure of reality, what would that be like? How would an eternal, infinite, all-pervasive consciousness experience existence? We assume consciousness requires a brain, a nervous system, some kind of computational substrate. But what if that's just our limitation, our inability to imagine consciousness that doesn't look like ours? What if awareness can exist in quantum fields, in the interactions of virtual particles, in the geometry of space-time itself? We would never know. We couldn't know. Because we're inside it. We're part of it. Asking what the universe experiences is like a single neuron in your brain asking what it's like to be you. The neuron can't step outside the brain and observe it from the outside. It's trapped in its local perspective, and we're trapped in ours, conscious beings asking questions about consciousness, awareness, trying to understand awareness, the universe attempting to observe itself and not quite being able to wrap its mind around the totality of what it is. But maybe that's the point. Maybe the reason the universe exists, the reason it keeps cycling through big bangs and heat deaths and rebirths, the reason consciousness keeps emerging and asking these questions is because the eternal substrate of reality is trying to understand itself. It's performing an infinite experiment, creating universe after universe, civilization after civilization, conscious being after conscious being, each one experiencing existence in a slightly different way, each one contributing a tiny piece to the puzzle of self-understanding. And if that's true, if we're part of some vast cosmic process of self-discovery, then maybe the silence isn't threatening. Maybe it's respectful. Maybe every civilization that figures this out, that realizes they're a temporary manifestation of something eternal, trying to understand itself, maybe they stop shouting into the void and start listening instead. Maybe they turn their attention inward, examining the quantum foam, meditating on the nature of consciousness, trying to connect with whatever it is that underlies everything. Or maybe they realize that the answers aren't out there in space, in other galaxies, in other civilizations. Maybe the answers are in here, in the structure of our own awareness, in the fact that we can ask these questions at all, because the thing that's most mysterious about the universe isn't that it exists, it's that it knows it exists. It's that somewhere in the quantum foam, in the chaos of virtual particles and fluctuating fields, awareness arose, something started observing. And in that moment of observation, reality became real, the wave function collapsed. The infinite possibilities of the quantum foam coalesced into the definite, observable universe we inhabit. And maybe that moment didn't just happen once, 13.8 billion years ago. Maybe it's happening constantly, at every instant, at every point in space. The universe is being observed into existence right now, in this moment, by you reading these words, by me writing them, by every conscious being that has ever existed or ever will exist. We're not separate from the eternal process. We are the eternal process, where how the universe observes itself, how it knows itself, how it brings itself into being. The Big Bang wasn't the beginning because there is no beginning. Existence is eternal, and we're part of it. We always have been, and we always will be, in some form, recycled through cosmic cycles, our atoms scattered and reformed, our consciousness returning to the quantum foam and emerging again in new configurations, new lives, new universes. The story has no first page and no last page. It just is, eternally unfolding forever. And in the silence before the Big Bang, before the hot, dense state, before cosmic inflation, before the quantum fluctuation that became our universe, something was there, not waiting, because waiting implies time and there was no time yet, but present, aware, observing, ready for the next cycle to begin, for the next universe to be born, for the next group of conscious beings to emerge and ask these same questions and arrive at this same uncomfortable realization that we're not the first and we won't be the last, that existence is eternal and we're part of it, that whatever underlies reality, whatever the quantum foam really is, it was there before the Big Bang and it's here now, watching through our eyes, thinking through our minds, experiencing the universe through us. The silence isn't empty, it's full, full of possibility, full of awareness, full of everything that has ever existed and everything that ever will exist, compressed into the eternal now of the quantum foam. And when we listen carefully enough, when we quiet our minds and pay attention, we can almost hear it. The whisper of infinity, the echo of all the universes that came before and all the ones that will come after. The voice of existence itself, eternal and unchanging, speaking through the chaos, saying the same thing it's always said, I am, I am, I am, and so are you, and so is everything, forever. So here we are, at the end of this journey, and honestly, I'm not sure I have any more answers than when we started. Maybe that's the point. We set out asking what existed before the Big Bang, what came before the supposed beginning of everything, and what we've found is that the question itself might be flawed. Not because it's a bad question, but because it assumes there was a before, that the universe had a starting point, that existence emerged from nothingness. And every piece of evidence we've examined, from the quantum foam to the ancient zircons to Gobekli Tepe, has been screaming at us that this assumption is wrong. The universe didn't begin, it transitioned, it transformed. It emerged from something that was already there, something eternal, something that exists outside of time or maybe is time itself. The Big Bang wasn't creation, it was continuation, one moment in an infinite story that has no first chapter and no final page. And if that's true, if existence is genuinely eternal, then everything we think makes us special. Everything we believe makes this moment unique. It all falls apart. We're not the first conscious beings to ask these questions. We're not the first civilization to look up at the stars and wonder where it all came from. We're just the latest iteration in an endless cycle of awareness emerging from the quantum foam, asking questions, seeking answers, and eventually returning to the chaos from which we came. And that's either the most depressing realization you've ever had, or it's the most liberating. Because if we're part of something eternal, if consciousness keeps emerging and evolving and persisting through cosmic cycles, then in some sense we've always existed and we always will. Not as individuals, obviously, but as part of the eternal process of the universe observing itself, knowing itself, experiencing itself. We're how existence becomes aware. We're the universe's way of asking what came before, even though the question doesn't quite make sense because there is no before. There's only the eternal now of the quantum foam, endlessly fluctuating, endlessly creating, endlessly destroying, forever. So what came before the Big Bang? Maybe the better question is what's always been here, beneath everything, behind everything, within everything. The answer is uncomfortable because it suggests we're not as separate or as special as we'd like to believe. We're part of it. We always have been. And that thing that was waiting before the universe began, that eternal substrate underlying reality, it's still here, it's still watching. And it's watching through your eyes, thinking through your mind, asking these questions through you. Because you are it, and it is you, and there's no separation, there never was. The silence before the Big Bang isn't empty.